Recién lo creaste vos, me parece. Por eso. Pum, pum, pum. Mm, parece- Será que nuevamente lo veo.
Hello. Well,
Yes, here we go.
okay. Well,
Okay, so let's go here again. This kind of things can happen. Welcome, everybody, once and over to Michael Betancourt's talk. While we are speaking in English in this moment in the Baches Plurinacional, it's because we are really dealing with this Baches and plural, and we are going to have today an English talk from the United States. Am I correct? From Michael Betancourt, and the chance to present research scientist at Simple Morphic is developing the methodological tools for supporting practitioners in inference. But he's not only on this part, so I like to present him as before being a statistician, he has a doctorate degree, PhD in the from technology, and he has been also collaborating and consulting from different analysis in the epidemiology, the pharmacology, and also engineering, ecology, and marketing. Hopefully, my internet was well enough for hearing this presentation and then keeping going. Michael Betancourt, thank you very much for being here.
Cheers. So let me thank I want to thank the organizers, Gustavo, Camila, Oksana, everyone who's had me here. It has helped set things up behind the scenes. I do want to apologize for not being able to speak Spanish. My Spanish is horrific, and while I could probably get by a little bit, I think it'd be a lot better here in English. If any questions do arise, I do have the chat window open, and so I'll try to address those as we go. I'm also happy to answer questions after the fact. My plan here is to do about 2 hours of lecture. We'll talk about a lot of pictures, a lot of concepts, and then we'll have about an hour of an exercise where we'll kind of see all these ideas implemented in a practical, if a little simplified, example. As we were talking about previously, the link to the exercise material is a notebook in HTML or PDF. You can find it on my website. I'll have a link a little bit later on, or you can follow it here. And Camila just put in the chat the Drive link that also has access to, it has the link and then has the PDF version as well. So feel free to grab that at any time to be prepared. So with all that said, let's go ahead and get started. The topic that I was asked to speak on today is generative modeling. And generative modeling is one of these interesting things that it has multiple facets, and depending upon what field you're in, people will interpret this term entirely differently. And so I want to talk a little bit about what the many interpretations of generative modeling, where they might arise, and I want to focus on one particular definition of generative modeling, which is more had to do with how we interpret models and how we use that interpretation to develop more sophisticated models that are more appropriate to our particular applications. So just some very high-level review here to make sure we're all on the same page. Bayesian inference is a mechanical way to quantify our inferences. That is, once we set our assumptions, we have this automatic way of quantifying which configurations of our models are compatible with the observed data. And the assumptions that we need are an observational model. We can think about this as a collection of probability distributions over the observational space, each of which tells a different story about how the data could have been generated. And then we complement that observational model with a prior model. And what that gives us is a joint probability distribution over both the observational variables and the model configuration variables. I'll use y for the data variables, theta for the parameters or the model configuration variables. And this joint probability distribution encodes all of our assumptions. In particular, our implementation of Bayesian inference can be derived entirely from this object. If I have observed data, which I'll denote with a tilde, I can evaluate the full Bayesian model on that observed data, leave the model configuration variables free, and that immediately gives me a posterior density function that I can then use to quantify inferences. Now, the tricky thing with a posterior density function is that that's not actually the end goal of an analysis. A posterior density function is a big high-dimensional object that we can't visualize directly. What we actually want to do in a Bayesian inference is extract various properties of that posterior, various insights. And the only mathematically valid way of extracting information from a probability distribution is with expectation values. So our general construction here is to assume an observational model, assume a prior model, assume that full Bayesian model, plug in data, get a posterior, which all happens automatically, and then we decide what kinds of insights we want to learn about, engineer an appropriate function, and then compute the corresponding expectation value. Now, this might sound a little bit abstract, but if you think about things like means, moments, variances, quantiles are derived from expectation values. All of these, probabilities, histograms, right? These are all various kinds of expectations. Now, the only challenge with all of this is that we can't actually calculate these expectation values analytically for most problems. We instead rely on numerical approximations. And this is where tools like Markov chain Monte Carlo come in. They give us a way of estimating these expectation values for various expectands f. Now, the more accurately we can approximate these expectation values, the more faithful our inferences will be. Think about the computational step is kind of talking to your posterior over a noisy phone line. Yeah, you're getting a message, but it's noisy, it's corrupted, and we want to make sure that we're actually understanding what the posterior is trying to tell us. This is one reason I get very particular about computation, because if we really want to realize the promise of uncertainty quantification and all these philosophical benefits of Bayesian inference, we need to have accurate computation and verified accurate computation. But let's take the computation for granted. Let's say that once we have a full Bayesian model, we know what to do. We have the tools, we know how to check that the tools are giving us something accurate. One of the main challenges in even getting Bayesian inference off the ground is, where does that full Bayesian model come from? How do we engineer a joint probability distribution, especially when we're talking about high-dimensional data spaces, high-dimensional model configuration spaces? You have a few hundred of these variables, it starts getting really hard to think about all of the potential ways they're coupled together, the behaviors might interact to give us this joint probabilistic behavior. And one of the ways that we can make this problem less overwhelming is to break it down into smaller pieces. And this is where conditional probability theory comes in. If I have a joint probability distribution over a lot of variables, I can always break that down into a sequence of conditional probability distributions. And the key is that these conditional probability distributions are all one-dimensional. They're all one-dimensional distributions, although they have these dependencies upon previous variables. Now, any ordering of the variables will give us a different conditional decomposition. There's not a single conditional decomposition, there's many of them. Some of these might be more useful than others. Now, before getting into what makes a good conditional decomposition, let's talk a little bit about how we can communicate this kind of decomposition, this kind of conditional structure. So let's say I have 5 variables. I have 2 data variables, and I have 3 model configuration variables. And I've ordered them in this way. So y1 comes first, y2 comes next, theta 1, theta 2, theta 3. This ordering is arbitrary. I can choose different orderings, but I've just chosen this one for example. What a conditional decomposition does is it goes in order, and it constructs a distribution for the first variable that depends on all of the previous variables. And we can visualize these relationships, not just with mathematical structure, but also with a graph. So I'm going to use a node, a circle, to represent every one of these variables. And I'll use arrows to denote these conditional dependencies. And in general, the first variable can depend on all of the other variables. And then the next variable can depend on the remaining variables, and so on and so on, right? So we're kind of peeling off one variable at a time to give us these smaller pieces that are a lot easier to reason about and allow us to then build up to these larger mathematical objects. So we go down the line. Our last variable, we assign it a prior model, just kind of capping off all these conditionals, and that defines this joint probability distribution. And again, we can think about representing this with these conditional density functions. We can think about it representing it with these nodes and these arrows. They both communicate similar information. Now, the real utility of this graphical model representation in particular is when these dependencies become a little bit simpler. So let's say, for example, that I have the same ordering of the variables. And sorry, I misspoke a little bit earlier. The ordering here is y1, y2, theta 3, theta 2, theta 1. So you can see the kind of progression of the variables there. So let's say that for whatever reason, the assumptions that we've made imply that y1 depends only on theta 2. It could, in theory, depend on all of the other variables, but we're making the assumption that it only depends on theta 2. This gives a much simpler relationship between some of these variables. Similarly, y2 might depend only on theta 3. Theta 3 might depend only on theta 1. And theta 2 might depend only on theta 1. So there's all of these possible relationships, but our assumptions might restrict which relationships are valid. And what's nice about this probabilistic this visual representation of our probabilistic model is that we can very directly see these relationships. Now, the graph here is not a complete representation, right? To define the full Bayesian model, I also need to know what the actual densities along those arrows are. But it's a really great way of kind of thinking about like outlining your model. What is the basic structure of your model? And then you can come in and fill in all of those details in a much more manageable modeling task. So I'm going to be using these graphical models a lot in this talk today to communicate these different structures. Depending upon the kind of graphical modeling that we're interested in, these structures, these particular conditional dependencies might be useful for algorithmic reasons, for computational reasons, or they might imply certain interpretations. And that will be a really key concept in just a few minutes. Now, another thing I just want to mention very briefly is that a lot of references that present directed graphical models or probabilistic graphical models, sometimes referred to as directed acyclic graphs or DAGs, they require that every node have a single variable. So we fully decompose all of our spaces into these individual component variables. Technically, these graphical model representations and these conditional decompositions don't require us to split everything apart. For example, I could keep y1 and y2 together as a single component, and I can keep theta 2 and theta 3 together, but let theta 1 be split off. And I could represent that with a graphical model where I keep some of these variables together. So this is kind of trivial in terms of the definitions, but some references won't allow this particular kind of graphical representation, and I just wanted to note that in case people are confused coming from other references. So I'm going to use this representation a little more generally than you may have seen before. All right, so we have our full Bayesian model. We have these mathematical decompositions into conditional distributions, and we have this probabilistic graphical model representation as a way of visualizing that conditional structure. As I mentioned previously, there are a lot of different conditional decompositions. In general, if I have n total variables, there's n factorial different decompositions, let alone think about the choices of those conditional densities. Some of these conditional distributions are going to be more useful than others. Some of these conditional distributions will facilitate certain kinds of algorithmic or computational operations. Some of them might offer different interpretations than others. And so when we think about what makes for a productive conditional decomposition, we need to introduce a criteria, not necessarily a quantitative one, more of a qualitative conceptual one for what makes a useful conditional decomposition. And I'm going to present two criteria here today. The first I'll refer to as procedurally generative modeling. And procedurally here refers to the fact that I'm looking for conditional decompositions that facilitate the implementation of some procedure, some kind of algorithm. One of the most common algorithms that we'll consider in Bayesian inference in particular is sampling. What happens if I want to generate a sample from this joint probability distribution, this full Bayesian model? I want to simulate a truth, and I want to simulate data generated from that truth. Well, one way of doing this is with ancestral sampling. So if I have a conditional decomposition, I can always generate a sample from the full model by following the progression of the decomposition. If I can sample from theta 1, and then I can conditionally sample y2 given theta 1, if I can conditionally sample theta 2 given y2, and then I can conditionally sample y1 given theta 2 and y2, that collection of sampled values defines a sample from the full Bayesian model. This is known as ancestral sampling. Now, some decompositions might make these intermediate steps easier than others. In theory, if you can decompose your joint model into one-dimensional conditionals, you can always employ things like rejection sampling, these brute force algorithms that will eventually get you a decent answer. But in practice, some of these will be more easier to implement than others. So they'll have faster algorithms or more efficient algorithms that you can employ. So the goal here is not to decompose the model into any kind of interpretable structure. The goal is purely to specify your model in a way that is easy to write in a certain programming language, that's easy to apply certain algorithms to, that's easy to sweep through computationally, depending upon what kind of algorithm you're interested in. And again, there's many of these conditional decompositions, and they all specify the same full model. So there might be many ways to implement a certain computation. And I think it's one reason to separate out the mathematical operation from the algorithmic implementation, right? MCMC is one way of approximating expectation values. It's not the only way. It's not the unique way. And it's not necessarily always the best way. Mostly it's the best way, in my opinion, of course. But it's something to keep in mind, that there's all these different representations of the same model, some of which might be more useful for computation than others. Now, there's a subtle related concept to all of this. Another way of generating samples, instead of just sweeping through a conditional structure, a conditional decomposition, is to sample from some auxiliary distribution, say a bunch of normals, and then transform those samples with a deterministic map. And that's what this operation here denotes. So a little bit more operationally, I sample from some auxiliary distribution. These variables x might probably have nothing to do with the thetas and the y's. They're just some convenient distribution I can sample from. But then I plug those sampled x's into this deterministic function. And if I can engineer this function correctly, then I get the desired samples out. Now, this particular construction is where machine learning gets its notion of generative modeling. So when you hear about generative modeling and machine learning and AI and these related fields, they're talking about this kind of generativity. They're talking about how to generate samples through this particular representation. And I want to emphasize this because the kind of generativity we're talking about going forwards has nothing to do with that algorithmic, in particular, this this push forward machine learning notation for generative. So I love the term generative, but I have to be really careful because there's a lot of communities that use these terms differently. We want to make sure we're talking using the same language. All right, so with that caveat out of the way, we can transition into the bulk of this talk, which is about what I'll refer to as narratively generative modeling. And this is where we assign interpretation to different conditional decompositions. And we want to choose the conditional decomposition that has the best interpretation, that actually follows how we think the system that we're studying behaves. And so what defines narratively generative versus procedurally generative is it has nothing to do with the computations that we can run, nothing to do with the mathematical properties of those conditional distributions. What defines narratively generative is whether or not that conditional decomposition tells a sequential story about where the data came from. And that sequential story will follow things like the underlying system that we're studying, the environment in which that system manifests, and all of the corruption and contamination that environment might endue. And then story has to also take into account how we're probing that environment, how we're probing that underlying system. All of these different behaviors get incorporated into this story. And so again, we can think about these different conditional decompositions as telling different stories for how we get to the same place. The simplest story that we have in Bayesian inference is that the data are generated from the model configuration variables. The data is generated from the model. That might sound trivial, but that already constrains the relevant conditional decompositions, right? We have to start with the probability of the data given the parameters. It doesn't make sense to talk about the probability of the parameter, theta 1 given y1 and y2 given theta 2, unless the story happens to progress in that way. So our kind of basic story typically decomposes as y1, y2 given theta 1, theta 2. And we can further decompose that story in various ways. For example, if I break up the theta 1, theta 2 node and assume that those two variables influence y1 and y2 independently of each other, then I'm telling the story that whatever behaviors are modeled by theta 1 and theta 2 don't interact. They're not coupled together. Whereas in this conditional decomposition, the story is that there's some behavior modeled by theta 1, and that behavior influences the behavior modeled by theta 2. And then both of those influences separately influence the observations. So theta 1 not only directly informs the observations, it also indirectly informs the observations through theta 2. And we can also have conditional structure in the observations, right? We might assume that the components of the observational space are generated independently of each other. But there might also be dependencies, right? Y2 might depend on the outcome of Y1. And we can encode that story, communicate it very efficiently using a conditional decomposition and these probabilistic graphical models. So once we specify what our model configuration variables are and what our observational variables are, and we have all of these different conditional decompositions, the one that's going to be most useful from a narratively generative perspective is the one that tells the story consistent with our understanding of the system. Sometimes you'll hear people throw around the phrase a mechanistic model. What are the mechanisms that are responsible for generating the data? That's largely a synonym here, but again, people use these terms differently and in inconsistent ways. So I'm going to stick to this data generating perspective and think about the processes involved in generating the data. And we can think about this in two ways. We can think about decomposing a full Bayesian model, and we can also think about building up a full Bayesian model from smaller pieces. And as we'll see in a little bit, that ability to build up a model from smaller pieces is a really helpful technique for trying to develop these models in practice. So a few very general properties of this narratively generative interpretation of conditional decompositions. The conditional structure, the conditional dependencies, the arrows between these nodes immediately tell us about the couplings, the interactions in that data generating story. What behaviors influence other behaviors? They don't say how they influence them. For that, we need to specify what the actual densities are along every one of those arrows. But it really captures this high-level summary of what's going on. And that allows us to very quickly identify things like the complexity of the model that we're dealing with, how well we can separate that model out, how well we can kind of localize certain behaviors. For example, here, theta 2 only influences theta 3. And so we can kind of isolate the story to just that theta 2, theta 3, and think about that separately from how theta 1 influences theta 3, or how theta 3 influences theta 4. But it also allows us to see when we have a really complicated model that's harder to break down into those smaller pieces. A model like this, even though it uses the same variables, or I guess similar variables, there's a few more variables here, the conditional dependencies are much more complicated. There's so many more arrows. And it's much harder to try to, say, pull out theta 4 and see what's going on there because it's connected to so many other nodes. So just visually, we can get a sense for how complicated a model might be. We can also get a sense for how inference works. Our full Bayesian model is represented by the full graphical model. And when I have data available, when I have values for the data variables, here y1, y2, and y3, the construction of the posterior corresponds to fixing those nodes to those values, right? I'm conditioning and filling in the nodes to represent that those correspond to known fixed values as opposed to unknown unfixed values. Critically here, we're not conditioning on the data and then propagating those constraints down through the graph. This conditioning happens all at once. And that's really important because if you try to propagate data, it ends up running into all kinds of inconsistencies and challenges. There's certain kinds of graphical structures that you can do that with. Most you can't. You end up with, these kind of inconsistencies where you have multiple messages coming into the same place, and there's no consistent way of combining that information together. So I really want to think about conditioning all of our data variables at once, and what's left will represent our posterior distribution. So we can use these models to represent, again, both the model, the story that we're telling, and our inferences. This will be especially helpful when we have different kinds of data variables, some of which might be observed, some of which might not be. Another point I want to make explicitly is the benefit of having procedurally and natively generative models at the same time. If I have a conditional decomposition that's interpretable, that tells a meaningful data generating story, and it also happens to be procedurally generative, then I can generate samples along that graph that also happen to follow the story. When I implement ancestral sampling, I'm not just generating values for these intermediate variables, I'm simulating the progression of that data generating story. People, including myself, tend to use sampling and simulation as synonyms, and they're really not. Sampling is a mathematical operation. It's something you do in probability theory, regardless of how you interpret the probability theory. Simulation arises when we have a data generating process, when we're using probability theory to model where data comes from. And so we really want, if we're going to use the term simulation, we want to keep in mind that we need this common structure. We need a conditional decomposition that we use for sampling and interpretation of the data generating story. And this might sound pedantic and perhaps a bit abstract, But there are cases in practice where there's one conditional decomposition that tells a story. There's another conditional decomposition that tells a different story, but is easier to work with in practice. And so you might use one decomposition to build your model. And then you might use another decomposition that specifies the same final model, but has a different interpretation of what happens as that story progresses, but it's easier to work with computationally. And these things happen, and we want to be aware of them so that we're not locked into one conditional decomposition when, say, we will go from building our model and we worry about interpretation to we go to implementing computation and worry about algorithmic feasibility. Let me stop here and ask, are there any questions?
At least not in the chat. There's somebody that wants to point a question at the moment.
For me, it's okay. I'm
Right.
curious. For me, it's okay. Yes.
Sure. Awesome. Again.
Yeah, I really love how you're going step to step, so that's great. Thanks for that.
Awesome. I do hesitate. I encourage people to ask questions. Please don't hesitate if anything's confusing, because we're going to be building on this stuff really quickly. And again, I'll be happy to try to answer questions afterwards as well. But I'd rather we fix things earlier than, and so that you can get most out of what follows. All right, so at this point, we've built up the basics. We talked about conditional decompositions from a mathematical perspective. We talked about how certain conditional decompositions are more useful for computational purposes, and how other conditional decompositions are more useful for interpretational purposes. Now I want to really take that idea of interpreting a particular conditional decomposition, having a meaningful set of pieces that we can use to build a model, and ask, what can we do with that? Well, the benefit of having an interpretable model, a model that tells an actual story that we think is relevant to the system that we're studying, is that we can start thinking about model building as storytelling. And what I want to do for the rest of the talk is think about various storytelling techniques and use them as analogies for very useful modeling techniques. And this analogy may or may not be helpful. And so if the storytelling is not very compelling, you can just focus on the modeling techniques in particular. But the idea here is to try to make this a little bit more comprehensible and connect to the things that we already do. Most of us are already used to telling stories in one way or another. Now, how can we leverage that for probabilistic modeling? So the first technique I want to consider is language. When we tell a story, we can tell that same story in different languages, right? And not just, different, English versus Spanish, the vocabulary that we use. I can tell a narrative very quickly in a very condensed form. I can also tell it using very flowery and potentially confusing language. Usually, when we're trying to communicate a story, we want to choose the right balance of the two. We want to include as many details as possible, but also make it as clear and concise as possible. And the same thing is true from a probabilistic modeling perspective. Only in a probabilistic model, our language is how we parameterize the two spaces, the observational space and the model configuration space. And here's just an example of that. Let's say that I have a model where I have a single monolithic model configuration variable. Not necessarily one-dimensional, just I've encapsulated everything into one variable. And I have n components to the observational space, each with their own component variable. Our first data generating story is the decomposition into an observational model and a prior model. But let's say that in this case, I also have a decomposition of that observational model into a bunch of conditionally independent observational models. This tells a story that these y components are generated independently of each other, so long as we know what theta is. And we represent that with a graphical model. So here's including all of the components together. Here's communicating the fact that they're conditionally independent, so they split up into these separate nodes that don't depend on each other, they only depend on theta. And we can also represent that with a plate diagram to just squash all of those nodes together with a square representing that we're duplicating that yn variable. So what we have here are a set of variables that are aligned or compatible with the data generating story. They allow us to tell this very simple story very concisely. But this is by no means the only set of variables that we can use to tell the same exact story. For example, I could reparameterize the observational space from these y's to a set of delta variables that are defined as the differences between those components. Mathematically, it's the same space. I've just coordinated it with different variables. Now, if I try to decompose the full Bayesian model using these variables, well, I get the same first step, but the second step is much more complicated because now these delta n's depend on each other. So to represent this graphically, let's say we have three y's, or three components. y1, y2, y3, they only depend on theta. That's a very simple story. Delta 2 depends on delta 1. Delta 3 depends on delta 2 and delta 1. I need to know those in order to get rid of those differences and isolate y3. So these are telling the same story, but the story on the right is much more convoluted than the story on the left. Now, this isn't to say that the y's are always the right picture. You might actually have a data generating story where there's increments that are generated independently of each other. Think of something like a time series. In that case, the deltas might tell a cleaner story than the y's. And the same is true in the model configuration space. There's various ways of parameterizing the model configuration space in any given application, some of which will use variables that correspond to particular behaviors, that isolate certain interpretable behaviors. And other variables might combine a bunch of behaviors together and lead to these complicated interactions. So it really helps when building our models to start by identifying the variables that correspond to certain pieces of that story, that try to that decompose the different behaviors of interest as best as possible. And that will help us tell a clean story. Another technique that's very common in terms of generic storytelling is what I refer to as serialization. And this just refers to the fact that stories are built of other stories. A play is built up from acts. An act is built up from scenes. Some of our famous narrative epics are built up from many, many books, many novels. Each of those novels are broken down into chapters. Each chapter is broken down into scenes or particular interactions. And so when you think about storytelling, we're never just dealing with one story. We're dealing with lots of stories built up on top of each other. And this has an immediate analogy when it comes to probabilistic modeling. I can think about all of my, say, model configuration variables as just one big monolithic space. But I also decompose them into smaller component spaces that isolate meaningful behavior. And those component spaces, I can further decompose. And what this allows us to do is take a big story that's just overwhelming and hard to reason about and break it up into smaller pieces that are easier to reason about. It's easier to think about the details. And so this recursiveness of storytelling gives us a really powerful technique for how to develop a complicated model. For example, I can start with the smallest pieces possible, tell just part of the story. That's a lot easier to reason about in isolation. And then I can expand that story, adding the previous chapter, adding the next chapter, and then adding the final chapter. So at any given point, I have a much smaller scope to worry about. At the same time, I can use this recursiveness to start by thinking about the broad story, an outline. And once I have that outline, I can start filling in the details piece by piece as necessary. And so what we get are these two different extremes for how we might want to build up a model. We can go from the bottom up, where we start with these smallest pieces from the beginning and start just building them together like Legos. Or we can think about a more top-down perspective, where we start with an outline and then we flesh out the details further and further until we get to the final level of detail. We're going to get to the same place either way. But the recognition, the acknowledgement that there's multiple ways of getting to that final story means that we don't have to get stuck in one place. If it's too hard to think about the overall story, let's zoom in and think about some of the smaller pieces. If the smaller pieces it's not quite clear how they fit together because you don't have a broader sense of what the overall narrative is, then zoom out. Think about the outline before digging in. A related concept with this is especially if we're taking the bottom-up approach and we're thinking about combining these small pieces, these small data-generating stories together into a larger story, we might consider how we compose those pieces. For example, we could just start thinking about different pieces arbitrarily, depending upon whatever happens to interest us that day, and just start filling in the story haphazardly. And so eventually the pieces get filled in until we have the final story. But the process and how we get there doesn't necessarily have any structure to it. It's just whatever we happen to have the opportunity to work on that day. For example, we might be working with a client or a collaborator who really understands the story that we don't. They might not be in every day. Or maybe you have different collaborators, different experts that you can contact every day. And so you might get a choice in how you piece the story together, which is fine. You develop pieces as you can until you have something that's sufficiently complete. But if you do have the flexibility, it's often a little bit more productive to not just try to fill things in arbitrarily, but to rather build up intermediate pieces. So here we're not filling in the whole story, we're filling in these 4 sub-stories. And once we have those sub-stories, then we combine those together. In other words, we can think about our storytelling, our model development, from a more modular perspective or a more piecemeal perspective. Either way, we're going to get to the same story. But again, we have these multiple paths of getting there. If it's helpful for us to reason about these intermediate component stories, then we can just work on building up those. And once they're done, we can snap them together into the full story. If at any given point we don't know how to proceed in that direction, it might be easier to just start thinking about the building blocks themselves and build those up before thinking about these intermediate component stories. Neither way is correct. They're all just different techniques that we can leverage in different situations. When it comes to storytelling, there's a lot of levels of detail that we can present to our audience. And the right level of detail is going to depend upon who that audience is. For example, if I'm telling a fairy tale, I'm not going to tell the same story to a toddler, to somebody in high school, and to a graduate student in humanities. I can tell that same story in 3 very different ways, right? I can have a very simple picture book for the child. I can go to a deeper, darker, more of a kind of the Aesop's fables that you might read in high school or middle school. And then you can go all the way to thinking about some kind of graduate exposition on the fairy tales and the historical context in which they were developed and how that gives meaning, interpretation to the story. All of these are the same story. But each of the tellings of that story are useful in different circumstances. And the same thing is true when it comes to probabilistic modeling. I can tell a very crude, simplified story. I can also tell that story with more detail. And I can tell that story with even more detail. There's always more features. There's always more behaviors that I can consider. But in practice, we're usually interested not in the ultimate detail. We're usually interested in the right level of detail for a given problem. Right? If I want to model how birds migrate, in theory, bird migration is a physiological process that depends on the climate and the environment of Earth, and there's a whole rabbit hole I could go down there. It also depends on the biology of the bird and the neurobiology, which requires molecular biology, which gets into chemistry, which gets into physics, which gets into particle physics. Like, it's just a ladder of detail. We don't need that level of detail. And so usually when we're telling a story, we want to identify what is the relevant scale of detail of interest and what features emerge at that scale. This is especially true in statistics where we're dealing with data. We only really need to model the level of detail that we can resolve with our observations. If you have really crude observations, you don't need a super complicated model because you're never going to be able to separate out all of those detailed behaviors. And one thing that's immediately motivates is thinking about building our models sequentially, not just in terms of structure, but in terms of detail. I might start off with a really crude measurement, and that crude measurement only needs a crude story. And I might follow that up with a much better set of data. Lots more data, much more precise metadata, different sources of data that allows me to resolve this underlying system with better detail. And to model that better detail, I might need to make my model more sophisticated. But to do that, I can take my simple model and fill in some of those details. I can use this top-down approach that we already discussed. And then I can continue this process iteratively until I have come to the complexity that is needed for a given application. And indeed, we'll see an application of this in the exercise. This is one of the most powerful approaches to storytelling, is instead of trying to tackle everything at once, is to start by telling a crude story and then iteratively incorporate more and more detail. Not only is that less overwhelming, but it's not only is that less overwhelming and more manageable, but it gives you a sense for when to stop. And usually you can stop much earlier than you might think. Now, it's easy to get carried away with this notion of narratively generative models and try to start separating out all statistical analyses into those that are narratively generative and those that are not. And unfortunately, the real world's a little bit more complicated than that. Just like you can have a story that crosses different genres and is hard to classify, we can have models that are both narratively and not narratively generative. So abstractly, let's say that I have these three components. The top component is narratively generative. For example, I know that these components of the data space are generated independently of each other. I know something about how they interact. And the bottom component, with theta 1 through theta 5, that's also narratively generative. That's derived from some underlying theory. But to connect the underlying theory to the observations, I might not understand what happens there. Maybe there's some complicated environmental process, or there's some potential contamination or corruption. There's an experimental device, and I don't quite understand how that thing works. And so the only way to bridge those two narratively generative components is with a more heuristic model. Maybe a non-narratively generative model that just specifies a bunch of mathematical patterns that are kind of, reasonable behaviors, but we don't really know where they come from or why they manifest. Just because one of these pieces is not as narratively generative as we might want it to be, doesn't mean we can't build a productive model. By combining that non-narrative generative component with a narratively generative component, we still get a broader sense of the overall story, even if some of the details aren't clear. And we incorporate what data generating story we do know. And we just repeat that, connecting, giving us this full story, which has a lot of narratively generative power to it, even if parts of it aren't as precise, as particular as we might want them to be. In other words, this phrase narratively generative, this terminology here, we really shouldn't think about it as a binary quantification or a binary qualification. Models are not narratively generative or not. Models exist in a spectrum of narrative generativity. And our goal should not be to have a perfectly, completely narrative generative model all the time. That's not always practical. Our goal should be to make our models as narratively generative as possible. So this might come across as a little bit abstract. So let's anchor it in a particular application. Let's say that I'm interested in modeling some data that arises due to a combination overlap of some signal and some background. Right? So I want to model that signal, but there's some irreducible background, some contamination that I can't get rid of. Now, I might have a theoretical model for that signal. It's, of course, what I'm interested in. So usually there's been a lot of thought about how that signal arises. So I have a narrowly generative model for that part of the model. But often these backgrounds don't get the same love. We might get a rough sense of what's contributing, but we don't really know how to model that. So we might throw down a heuristic. So say our model here might just be a polynomial model with some restriction on the kind of behaviors that are reasonable. Even though that's a completely heuristic model, we don't know how those polynomial shapes arose from some underlying, from the environment. We can still combine that heuristic background model with the signal model, eliminate or somehow detrend or remove the contamination from that background, and isolate meaningful inferences about the signal. So narrative generativity is really powerful. I love it. It's fantastic. I apply it to everything I do. But we can't be precious about it, because there are absolutely going to be applications where parts of the story can't be told with in a principled way. And that's okay. Tell your story as cleanly as you can, get the outline as fleshed out as possible, get as many details in as possible, and whatever is left, you model as well as you can. So far, I've been referencing a data generating process. And in practice, there's no reason why a model can't incorporate more than one data generating process, right? Just like some of the most exciting, engaging, compelling stories that we encounter, they don't just tell one story. They don't just tell one narrative. They weave together multiple narratives. They tell part of one story and then jump to another part of the story. And at some certain places, those stories might intersect and then they diverge again. We can do the same thing in probabilistic modeling. A full Bayesian model and a narrative generative decomposition of that full Bayesian model can be interpreted as incorporating two different data generating processes, if not more. So for example, here we can think about this as a single data generating process that generates Y1, Y2, Y3, Y4, and Y5 all at the same time. But we can also think about this as one data generating process that gives us Y1, Y2, and Y3, and a second data generating process that gives us Y4 and Y5. The joint model that combines these together allows us to incorporate all of these disparate sources of data together at the same time. If you've ever heard about a problem like data fusion, people say, I have all these sources of data, I don't know how to combine them together. The way you combine them together is to build a consistent joint model of the data generating processes responsible for all of those different sources of data. And so long as the behaviors that they share are properly accommodated, so long as the interactions between separate behaviors are modeled appropriately, you can combine all of those data together, and your posterior will automatically incorporate the couplings and interactions and complicated dependencies between all of those behaviors. Now, when it comes to actually building a probabilistic model that incorporates multiple data generating processes, we have, again, multiple strategies. We can start by building one data generating process. And then when it comes to reasoning about the second data generating process, we might think about branching off. At what point does the second data generating process start incorporating its own unique behaviors and then its own data? Sometimes, however, it's more helpful to think about these the separate data generating processes on their own, develop a model for each, and then combine them together by identifying which behaviors are shared and merging those into the same nodes. Either way, we'll get to the same model, and again, we can take advantage of those multiple paths to make sure that we're using whichever one might be most productive in a given circumstance. Now, I just want to go through an explicit example of how we can take advantage of this, because I think it's not always obvious just how powerful this is. So let's say that we have this model. There's two components of the observational space, y1 and y2, and we have three model configuration variables. Now, we can think about this as a joint model of two data generating processes, or I can think about this as two separate data generating processes. There's this data generating process where I generate y1 from theta 1 and phi, and then there's a second data generating process where I generate y2 from theta 2 and phi. Now, one of the wonderful theoretical properties of Bayesian inference is that I can combine different sources of data together sequentially. So in this case, what I could do, at least in theory, is I can take the first model, I can condition on the data, and that gives me a posterior for theta 1 and phi. I can then marginalize that posterior to get a marginal posterior for just phi on its own. Right, and this is important because phi is the only thing that informs the second model. Theta 1 is irrelevant. So now if I want to incorporate the second set of data, I can take the second model and replace the prior with this posterior for phi. And then I run the Bayesian updating again, I get a new posterior, and I get a consistent set of inferences for theta 2 and phi. And of course, I can marginalize that to get a posterior for phi that incorporates both y1 and y2. Now, in theory, this is all fine. The problem is that the intermediate step here is this marginal posterior density function, which is not something we're going to be able to construct in practice. So this is one of these lovely kind of conceptual ideas, but it really doesn't manifest in practice. But we can get to the same place without going through that intermediary that we don't know how to work with. All we have to do is, instead of thinking about those models separately, is just work with the full Bayesian model all at once. Take the full model, plug in all the observations, and that will immediately give us a posterior for all of the variables given both those sets of data. The posterior inferences here are exactly the same as what we'd get using that two-step process, only we didn't have to go through that intermediate step that we don't know how to implement. So anytime you're dealing with multiple sources of data, all you have to do is think about that joint model, and then the implementation of Bayesian inference follows exactly as it would with any other analysis. A corollary of this is what happens when we want to make predictions that aren't exactly the same as the data that we've collected. So usually when we're talking about making predictions, we're just assuming that we're going to repeat the same data generating process again. We're going to repeat the same measurement, repeat the experiment. So I'll have some observed values of y1, y2, y3, and I want to see what happens at the next realization of this. What does the next y1, y2, y3 look like? That's what kind of most of the math focuses on, I should say. In a lot of industrial and scientific applications, however, what's much more relevant is generalized predictions. What happens when I want to know something about, say, y4 and y5 that come from a different data generating process that shares a lot of the same behaviors as the first data generating process, but it's not exactly the same? How do I accommodate that difference? Well, from a narratively generative modeling perspective, I just build the full model. I evaluate what I know, which in this case is y1, y2, y3, and all in one step, I will get this just kind of joint posterior that captures the uncertainty in all of the parameters and the unobserved predictive variables. So I'll get a posterior over theta 1 through theta 11 and y4 and y5. And I can use that constructive predictive distribution for these new variables. So again, just an example of this. So I have that same full Bayesian model. And now let's say I want to observe y1 and make a prediction for y2. In theory, I can do this sequentially. And this is what you see in a lot of introductions to Bayesian inference. So I just look at the first model, I plug in the data, I get a posterior, and I marginalize out theta 1 to get a marginal posterior for phi. I can then use that marginal posterior for phi as a prior to construct a predictive distribution for y2. So in other words, the kind of the prior predictive for y2 becomes the posterior predictive when I plug in this data dependent prior. But just like we had before, the obstruction here is that we need this marginal posterior density for phi. We need a closed form for this density. I need to be able to evaluate this for arbitrary values of phi. Not just a single number, I need an entire function. Not something we're going to be able to get out from any of our computational tools. But in practice, we don't have to do that. If I have the full Bayesian model already, then I've done all the work I need to do. I write the full Bayesian model down, I plug in the data we happen to have observed, and automatically, by magic, what I'm left with is a kind of joint posterior for theta 1, theta 2, phi, and y2. And then if I can project out just y2, I get that predictive distribution. So once we're comfortable with building a single data generating process, it's pretty straightforward to start thinking about multiple data generating processes. And that's where we really start to open up the power of this perspective. We're not only incorporating all of the relevant behaviors in a single data generating process, we're able to combine these multiple disparate sources of data together. This can lead to much better uncertainties because we get a lot of information that can complement each other. It's going to allow us to compare and contrast different circumstances better, see what happens in different locations, see what happens at different times under different circumstances. Now, related to this is this notion that I'll refer to as causal inference. And I mean this as sarcastically as I can. The term causal inference...
Michael, allow me to interrupt you there a second. Can you come back to the previous slide, please? So, yeah, my question here will have then this independencies of these posteriors. Can you really make them independent? So, because we were seeing also that in this combination somehow y1 and y2 might be a response, just a combination not able to really split it or to correctly identify that one part is related to one explanation, let's say, or belongs to somehow one of the features, and other posterior will belong to the other one. So I can understand this powerful tool of combining them, but get into back. How are you able to separate them? You have them on a real ecosystem, for example.
Okay, so you're breaking up a little bit, so I'll try my best and let me know if I may have misunderstood.
Sorry for that.
No worries. So the reason that we can separate out our kind of our posterior inferences in the first case and our posterior predictions here in the second case into a two-step sequence is entirely because we get this. We can think about our observational models decomposing into an observational model for y1 that depends on theta 1 and phi, and then a separate observational model that only depends on phi and theta 2. And so the key here is that there's no arrows connecting y1 and y2. And so that implies there's a certain decomposition of the observational model, and that means I can take one likelihood function first, and then a second likelihood function next, or I can combine them all together at the same time. So it's absolutely a consequence of this particular structure.
Okay, so it's correct if I am interpreting that from one data, then I will have like two chances of two different posteriors, depending on two different models. And then in this case, we have everything all together joined.
Yeah, so I could consider, right, so let's go back to the top here. I think I have the right slides for this. Yeah, so I have the joint, model, and then I can think about these as two completely separate models. I could construct posterior inferences for y1 using this model. I can construct posterior inference for y2 using this model. I can't combine those posteriors. That doesn't work. What you can do is, kind of learn from y1 and then incorporate y2, like I went through here. And that relies on the fact that there's no arrows between y1 and y2. So I actually write out, like I'll do it here in the chat. The math here is if I have...
Okay. And
go ahead.
Yeah, and I got that. Then that's clear for me. So then in the next step, it will be more safe somehow and making them also joined, but keeping them together. So you were having in another slide, so it's y1, 1, 2 together as a prior. Sorry, as a posterior.
This one?
No, one more. An extra. Yeah. So in that case, where you have all together as a complex model, then you're having the y1 and the y2 as a posterior all together.
Well, in this case, we've only observed y1 and not y2. So y2 basically becomes indistinguishable from the model configuration variables. I'm trying to predict y2.
It's fine. Just keep it going and then maybe I'll keep a question. Thank you.
Sure. So I think one thing I do want to kind of comment on is I like once you start trying to break down your inferences and predictions into these sequential steps, it gets really confusing really fast. You can't always do it. You have to actually, like I put the equation here in the chat. For this model, I get these two separate components, the observational model, which I can think about as generating two different likelihood functions. And it's in that case, I can combine them sequentially, but you can't always do that. And people make a lot of mistakes where they'll take two sources of data, construct posterior inference for them, and just try to combine them together in inconsistent ways. It happens all the time. And one of the big takeaways I would argue here is that you can avoid not just the mathematical problems potentially, but all of those conceptual confusions, those points of those opportunities for getting tripped up about, well, can I do it here? Can I not do it here? You can avoid that entirely by just always working with the full model. Just build the full model, plug in what you know, leave what you don't know fixed or free. And then what you're left with will be either consistent posterior inferences or consistent posterior inferences and predictions, or just predictions. It all happens automatically. It's the beauty of all of this. And so it's a really an important point here that it's worth emphasizing, is that it's, you can look through this and kind of go like, all right, I get the full Bayesian part. That seems straightforward. These other parts are a little like, when can I do that? When can I not do that? Why can we do it here? I completely agree. Those things are super complicated, and I always mess those things up. I always have to sit down and kind of rederive things by hand in certain cases just to make sure things are correct. And it's the reason I love this full Bayesian modeling perspective, is that you don't have to deal with it. You just do everything at once, and you split up your modeling and your computation as these two separate steps. So yeah, so it's an important point. Okay. So this part will probably get, potentially get a little controversial depending upon where people are coming from. A lot of the contemporary statistical practice, including data science and machine learning and these kind of related fields, you're hearing this term causal inference more and more. And there's a lot of, but it's easy to kind of confuse causal inference with data generating processes and this notion of narrowly generative modeling. Unfortunately, the way the term is actually used and the methods that are being described as causal often have nothing to do with what we've been talking about so far. So I just want to spend a little bit of time talking about how we kind of might formally think about causality, how it's actually used in practice, and where narrowly generative modeling fits in to both of those perspectives. So from a storytelling perspective, causality is really quite natural, right? What is a story but a series of causes and effects? Something happens, and then that causes something else to happen, and then there's a further event that is influenced by those previous events, and then we have a final event that concludes the story. In fact, there's a lot of dictionary definitions that will define a story or a narrative as a series of causes and effects. So it's a pretty natural concept. And if we know our story deep enough to break it down into the sequence of causes and effects, behaviors that one behavior influences another behavior, that influences another behavior, that finally influences the data that we generate, we can take advantage of that knowledge and use it to motivate a compatible narrative generative model, where each of our variables that model these intermediate behaviors follow that causal story. And so from this perspective, causality and narrative generativity can very much be thought about as two sides of the same coin. You might not always have pure causality. Again, there might be these non-narratively generative components in your story, totally fine, but you want to kind of make sure the overall arc is as causal as possible, and then all of those intermediate pieces are as causal as possible. Unfortunately, this is not what causal inference means in a lot of fields. It's hard to try to summarize or reduce this down to a single concept, but my best attempt is that when people use causal these days, they're almost always referring to some change in how the data was generated. So we can think about, another way of thinking about this is our data generating process fixed? Is it static? In which case the predictions that we want to make follow exactly from our inferences. Or is there some kind of dynamics involved? Can the system that we're studying change or evolve in between when we've collected the data and we want to make a prediction? And there's various vocabularies for this across the different fields. People will use everything from extrapolation to out of sample generalization, transfer learning, model or concept drift. All of these terms are kind of getting at the same basic idea. Something has changed, and so your naive predictions aren't really going to match what you might see going forwards. And what these methods then do is try to accommodate some change without necessarily modeling the actual causal structure. In other words, they're modeling the effects, or they're trying to heuristically model the effects, but not the causes. So it's not really causal inference because there's no mechanism, there's no process there. It's just heuristically modeling, oh, I think that the data generating process might change, and that might manifest as, a different slope before and after. Okay, so I have a model with two different slopes. Is it really modeling why the slope is changing or how the slope is changing? Nope. But it's allowing for some variation. If this is how we want to interpret causal inference, which I don't think is a helpful description, by the way, and again, I'm just being really idiosyncratic here and iconoclastic, and I recognize that. But if this is how you want to interpret causal inference, derivative generative modeling is still very useful for this. Because all we have to do is model a data generating process that's responsible for the data we've observed, and then model a data generating process that's responsible for what we haven't yet observed. Sometimes these will be the same. If our data generating process is static, then we're going to have the same basic structure. We can build a full Bayesian model that includes both the observed variables and the predicted variables. And then we apply Bayesian inference, right? Which is always plug in the observed data, get your joint posterior for the model configuration variables and your predicted variables, marginalize out those model configuration variables, and that gives you this predictive distribution. What do we think is going to happen in the future, given what we've seen in the past? The same exact thing happens if our underlying data generating process changes. We just start with one data generating process, and then we use a different data generating process for our predictions. But we've already seen how to combine two data generating processes together. We just build the consistent joint model. And it's the same mechanistic Bayesian inference at this point. You plug in what you've observed, you get that joint posterior, you marginalize out the unobserved variables, and you get this predictive distribution. So whether or not you want to think about causal inference as actually referring to causal structure and causal mechanisms, narrative generative modeling, incredibly powerful for that. Or if you want to think about causal inference as just modeling heuristic effects and the potential outcomes without really knowing what those causes might be, narrative generative modeling is still very useful. And so one of the reasons I really like narrative generative modeling is it kind of just abstracts everything away. There's not different kinds of models. There's just modeling. You tell a story. What story are you telling? How causal is that story? How detailed is that story? How heuristic is that story? They're not different modeling approaches. They're just different kinds of stories. So let's say that we do have some kind of dynamics in our data generating process. What could be causing those changes? Well, sometimes we're not in control of the system. The system evolves in a way that we are not able to prevent. So let's say that, for example, we're trying to model prices in a market. Well, sometimes new goods are going to enter into that market that are less expensive, and more expensive goods might leave that market. And so the overall population of prices shifts. But we're not responsible for that. We can model how it's happening. We might model why goods are leaving, why goods are entering, how they do so, and that gives us a way of incorporating what might happen in the future. But sometimes we can directly control what happens. The data generating process changes because we intervene. And so in this price example, we might be a company that has lots of products in the market, and we might actively discount them, changing the population of prices. Regardless of why the system is changing, our modeling approach is the same. We just want to model what that change is. How is that system evolving? And so when it comes to something like modeling an intervention, what matters is not what's being intervened on. What matters is what's the consequence. How is that intervention being implemented? And there's no unique answer for this. So we might have this data generating process before intervention. We might have this data generating process after intervention. Once we have reasoned through those processes and we're confident in our assumptions, again, we build that joint model, we plug in the data, we get our inferences, get our predictions, etc. But the question is, how do we model interventions? And this is another point where I think there's a lot of confusion in the community. A lot of people will interpret intervention as just fixing a variable. If I intervene on theta 1, the value of theta 1 gets fixed. But that's not always how things happen. Oftentimes, there's side effects. You try to intervene and fix theta 1, or whatever, you fix whatever behavior theta 1 is modeling, and that might lead to some other behavior popping up that you didn't expect. Sometimes modeling interventions is as simple as conditioning on your model, as if theta 1 was observed. But a lot of times it's much more complicated than that. And the only way to differentiate these is to make assumptions, is to understand what's going on when you intervene on a system. This is even more complicated when you think about intermediate variables in our graph here. If I want to intervene on theta 3, does that intervention just fix theta 3 and cut the arrows going into theta 3? That's one possible intervention. But for example, the influence on theta 1 might then redirect from theta 3 to theta 4, right? Maybe theta 3 was preventing or blocking some influence, some relationship that was already there. And again, there might be these side effects that have nothing to do with theta 3. But just when we try to intervene on theta 3, there's these unintended influences on other parts of the data generating process. And so using the kind of nomenclature that's become very common these days, there's no such thing as a do operator. There's no mathematical operation that tells you what happens when you intervene on a system. There's many possible consequences for intervention. And the one you want to consider is the one that you happen to think is relevant. Intervention is a modeling problem, just like everything else. And so again, the reason I'm really hammering on this is not, well, I've been a little salty about a lot of these methods, but I think from a predictive perspective, it really helps to avoid a lot of this vocabulary and this jargon and just think about where the data came from. Once you start focusing on the stories and where the data is coming from, we don't have to worry about, is this causal, is this not causal, is it this, do I use this estimator, do I use this black box? Just tell your story. And then Bayesian inference will do the rest. Especially when you have probabilistic programming tools where you can write up your story as code, and then all of the Bayesian inference can happen out mechanistically. Right? You don't always get a good answer out. In fact, we'll see that in the exercise. So we have to be careful to make sure the Bayesian inference is being implemented appropriately. But it's all pretty straightforward at that point, right? The hard part is getting to that model, getting to that story. And the final technique I want to mention here is just how much can we trust a story? Stories are great. Stories can be compelling, exciting, and entertaining, and they can also be complete BS. So I'm using Cliff here from Cheers as a classic example of someone who tells a really good story that's completely false. The same thing is true when it comes to probabilistic modeling. You can build up a probabilistic model that tells a really compelling story. It might be really elegant. It might be very exciting what would happen if it were true. But none of that means that that model's correct or useful. Just because you can tell a probabilistic story doesn't mean that probabilistic story is going to well approximate the system that you're studying It doesn't mean that's going to be good enough to get the kind of insights and inferences and form robust decisions and predictions that you're interested in. So the first step is to tell our stories, to build our models. But then we have to be really careful to validate those models, critique those models. What could be wrong? What could we be missing? What features might be too rigid? And then when we plug in the data, look at the consequences. Compare what our model thinks the world behaves like to what the data looks like. We'll see this in the exercises, or refer to this as a posterior retrodictive check, because we're retrodicting what we've already seen. And we just want to make sure that our model can reproduce the data we've observed. And you'd be surprised how often they can. Now, it's not the end of the world, because if we get to the point where our story isn't sufficiently robust, isn't detailed enough, then all we have to do is expand our story, add some more complexity, add another chapter, add another scene, iterate, and see if we've improved the situation, using the structure of that failure to motivate not just the fact that we need a better story, but what was lacking about the initial story and what kind of features, what kind of narratives should we add. So once you start kind of getting into narrative generative modeling and things start clicking and you see that your models are actually consistent with your understanding of the system and the details of the measurement and the experiment and how things are actually working, it's so easy to just take everything for granted at that point. But we have to be careful. We have to be rigorous to check just how good that model is, because we are responsible for making sure that that is not just a compelling story or an elegant story or a beautiful story, but a useful story. And again, we'll see all of this implemented in the exercises. So before breaking for questions, we're at the end of the lecture. So I just want to mention again what we'll be doing afterwards. If you go to my website, if you haven't seen the link already, if you go to my website, there will be a section called Case Studies, and then there'll be a heading called Inferring Customer Conversion. There's an HTML and a PDF. Pick whichever one you think is most useful for you. And I'll be going through this. This will go through a progression of models, each based on a single story, but adding complexity based on the failures of the previous models. And we'll use these narrative generative ideas to expand that story, to expand that model into something that's adequate. And then just a quick plug, if you are interested in this and want to learn more, I have not just about these topics, but other related topics. I have a lot of writing on my website, everything from probability theory to Bayesian inference and modeling to particular modeling techniques. If you want to follow me on the socials or a mailing list, I have a monthly mailing list. I have a bunch of socials, and also have a Patreon if you have the resources that are interested in supporting. So with all that said, are there any questions I can address about any of this material, either in the abstract or even applied to a particular circumstance?
So far, I think that thanks very much for the explanations given up to the moment. I don't know if you have received already the links and if everybody to open them without any problems.
We don't hear you very well, Camila. I am 100% agree with your presentation, with your arguments. Are really good talk. Thank you very much.
Cheers. Thank you so much.
I don't have any question, indeed, because I'm
okay.
Agree with you, indeed.
No worries. No worries at all.
There is no do operator.
Yeah.
Indeed, should Perl tell this. They all when we read this causal, there is an author that talks about causal inference, that is Perl, and he used this concept of do operator, that when we intervene the world, we are changing the mechanism only in this variable. But he also says that these change are also probabilistic. We change the probability, the conditional probabilities when we intervene. So maybe Shudaparl will be agree with you. I don't know.
Yeah, I don't know. There's enough wiggle room that you can argue that some of these ideas are consistent, but I think when it really comes to the implementation,
it is important.
As much as they might say that, like, oh, this is really general, it can handle all of these things. Like, okay, but what are you actually applying it to? And in my opinion, it's always these like really simple examples that don't generalize, and the tools don't go beyond those simple examples. So, philosophically, conceptually, yeah, maybe, but I'd rather have tools that are much more clear about how far they can go, what they're assuming, what they require you to assume, and the like.
Yes, an intervention is simply a different history, a different story.
Yeah.
So is this we must rethink the story. Yeah,
I think a lot of the ideas I talk about here, they might sound kind of trivial to some, and I think that's totally expected. A lot of these ideas are extremely common, and they're just basic intuition in a lot of scientific fields, for example. All I'm really trying to do here is use the storytelling and analogy to organize them together into a somewhat consistent framework. And just to see that, like, a lot of these ideas that we have from, say, scientific fields or even some industrial fields that have developed a lot of these ideas on their own, that they're useful. This intuition, domain expertise absolutely should be part of your model. And these people going around saying that, like, you just apply an algorithm and don't ask any questions, they're the problem. You're not the problem.
Yes.
So we have a question in the chat from Charles.
There is a question.
Asking, could you expand on your comments about how each discipline has their own pet interpretation of causal inference? I'm familiar with economics. Causal inference equals economic theory. It's econometrics. In the Rubin model, model-based inference, how else do you have in mind? So I would say even the Rubin model, like, okay, so there's how people, just as Gustavo and I were talking about, I think there's how people will, like, present causal inference in, like, over a beer, or like in the first day of the lecture they give. I think what really matters is, like, the next day, because if you might have an economist or econometrician, saying things like, "Oh yeah, it's all this causal inference stuff, and I believe in this and this and this." They're like, "Okay, but what are your models actually?" And they're like, "Oh, I did a regression with differences on the slopes." And you're like, "Okay, that's what you mean by causal inference. You're not modeling, why there's variation in those groups. You're not modeling the treatment, etc." I would say the closest thing in the economics arena to what I'm talking about here would be something like a natural experiment. What's a natural experiment other than saying, "Oh, I'm assuming something about the data generating process, and because of what we know about this system, I can use this simpler story, this simpler model, and get these generalizable insights." That's awesome. That's exactly what we're doing here, but we're not, limiting it to this very narrow interpretation. Same with, like, a lot of the Rubin stuff. I think, like, read some of the papers will be like, by the way, just bad dude, but that's a separate story. A lot of that stuff will, like, the first few paragraphs, like, sound very compelling, and then you get to the actual results, and it's just like, like y1 minus y2. It's very, you get very similar differences in a lot of cases. And so, whether you want to say that it's the philosophy or the interpretation that differs, or it's the implementation that differs, I think what you actually see labeled as causal inference are things like differences in differences, P-score. I can't remember the name. It's completely blanking me at the moment what the P and P-score is. Not proximity score. But, the weighting of the covariates to try to match things. Average treatment effect, which is okay, but how are you calculating it is what matters, not the thing you're calculating. I've heard people say things like, oh, I went from a linear regression to a nonlinear regression, so it's causal inference now. Okay. And then you get the whole like Pearlian perspective, instrumental variables. Like, I think there's that gap between the again, that high level conversation and then what's actually implemented. And I think that so many fields are really defined by these rigid implementations that it's one thing if they did them once and then tried other things, but they get stuck in these things, and that becomes the convention in the field, and that effectively defines what causal inference means in that field. So that's how I would define it. I recognize it might not be a universal definition, but what matters for me is how are these inferences being constructed, how are they being implemented, and how easy is it for people to implement these ideas as well. So it's not just a theory for me, it's how that theory manifests in practice. And so that biases how I present this, absolutely.
Michael, one question. You're familiar with the gates, first of all, factor graph notation. There is the gate notation in the factor graph. The causality with gates is a paper written by Wynne, a team that came from Bishop, Joseph Bishop. I think it is useful I think the power of causal models is this notion of the dynamics. Maybe there is some an individual, for example, that makes an intervention, but we can model this in one single generative model, in where we are modeling this intervention as a variable, for example. So, as you are talking that it is important to have one single model, I think this is useful. And these models that are dynamic, because the causal models are dynamic, if something happens, this model changes, and will predict these models that are dynamic has the advantage that can predict this change in the world. So are predictive, are better in predictions in general.
So I'm not hugely familiar. Sure, no, absolutely. I'm not hugely familiar with the causal gate stuff. I've heard of it before. I haven't done a super deep dive into any of it. But I'll use the factor modeling as an example here. I think the benefit from something like a factor modeling perspective, or the lack of benefit for me, is that it's really hard to say anything about how the individual nodes in a clique are behaving, because that's what the factor graph is doing, right? It's kind of like aggregating certain behaviors together, which makes it difficult to pull out these individual behaviors. Now, there might absolutely be circumstances where, an intervention influences a clique and only a clique, in which case the factor model variation might be a very straightforward thing. But for me, because it's hard to kind of tell, you're kind of thinking about the clique as this monolithic thing, it's hard to reason about the dynamics within that clique, or the various cliques that you're working with in the factor graph. And I think, a corollary of that is when you start doing message passaging on factor graphs, very few factor graphs will actually allow you to have consistent results.
Yes.
And so you end up getting these kind of this happens and then this happens, and how do you make that consistent? Well, that's where it gets, tricky. So what's nice about
these inconsistencies are because we must propagate, iterate to get to converge the inference. Is that the question?
Yeah. But the point is that those messages don't correspond to data generating processes. They're not interpretable as a story because it's this incomplete bit of information that's getting passed, right? Exactly because of that. The advantage of the direct graphical model representations is that you get this sequential picture, and that sequential picture allows you to isolate these individual pieces separately from each other. Factor models and thinking about cliques, you know, you have to think about these larger, more involved pieces. And I'm not going to say that those pieces can't be useful. Sure, absolutely. I would say it's, for me, at least in the exercises I work with, or the applications I work with, I would say it's less likely that those kinds of structures would be compatible with the kinds of data-generated stories of interest. But yeah, it absolutely could be. In which case, these could be quite useful.
I think factor graphs and Bayes networks are the same thing in the same specification of the same mathematical specification of the joint probability distribution. Indeed, they're both are generative models. Indeed.
Sure. Well, I would argue factor models aren't really generative in either sense, but we can discuss that offline. I think so there's the question about like, what is it, like IMAPs and like there's a subtlety whether or not they actually model the same spaces of models, and it's going to depend upon how exactly you interpret the nodes, whether the nodes are individual variables or can have multiple variables, and it gets real annoying. I would say even if they can be used to model the same classes of models, or to represent the same class of models, I would still argue that the directed graphical model representation is easier to connect to our domain expertise, and that's really I would say, it's the operative goal here. That's the priority.
Okay.
And factor models might facilitate computation in certain cases.
Mm-hmm.
Similarly to how other conditional decompositions besides the narratively generative one might be easier to work with in terms of sampling. But for me, that would imply starting with the narratively generative picture,
yes,
and then once you have that full Bayesian model, turning it into a factor model,
yes.
Using the factor algorithms and the like.
I am agree. Okay.
Sure.
There is some other questions here, because then we have some exercises to play.
Yeah. So what I would say is, because I've been talking for 2 hours, and I'm sure that's not great.
10
for
minutes
everyone.
of break here. I think.
Yeah, let's do 10 minutes.
10 minutes.
And so everyone can get a glass of water, go to the bathroom, walk around a little bit, and then we'll come back and I will start going over the exercises linked here. So get those opened, have a few minutes, and we'll come back and say in 7 minutes.
Okay. So
cheers.
Yes, thank you, Michael. Maybe now everybody can hear me better. I was also wanting to point out that if anybody wants to say something in Spanish, then we can translate it. So,
okay, that's good. Se puede hablar en español.
Si alguien quiere hacer alguna pregunta en español, háganla y se la traducimos para Michael. Quizás eso también pueda facilitar en algún momento. Thank you very much, Michael. I really like the talk. It was very clear how we can find and to keep going step by step. It really kept me in a safe. Okay, we don't need to know everything. We can know a bit, and then just join and merge with something else. So I really like that. So thank you very much. And repeating what you. Let's have a break of 7 minutes, more or less, and come back here. Anybody have a problem with the download links? Just let me know. Thank you.
Thanks, Milo. All right, see everyone in a few minutes.
Yes.
Sube la marea, sube la marea.
started,
Yes.
because there's plenty to talk about.
We are.
So the interesting thing with this lecture is what I've been giving a lot of them in my private courses, and it ends with an example, but a purely kind of a high-level one, where I talk about a particular application and show some graphical models representing some more and more complicated stories. But there was some requests for some stand code, so I also, kind of in a wild rush, was able to put together this notebook where I implemented these ideas in explicit models with data and everything. So if there's anything confusing in the text, it may not be unexpected. Just let me know. It'll definitely be iterating, fixing it, and it'll always be up on my website. So our story here, I guess the challenge with generative modeling is that it relies on domain expertise. And domain expertise is something that's very individual. Every one of us comes from different experiences. We have our own understandings of things. And so there's not going to be any particular example that's, universal for everyone. So what I'm going to do here is present a pretty simplified, abstract example, but one that's sufficiently concrete that we can see a lot of these ideas implemented. And so the basic idea here is that we want to understand how customers engage with a certain business. The example I'll use here will be people visiting a website. So we have potential customers coming to a website. And I'm intentionally using terrible clip art and bad animations here to try to get us into the feel of business and industry. People who have come to this website will then do something. They might look at some pages, and there's a chance that maybe they'll do something profitable. Maybe they sign up for a mailing list, or they purchase a product, or they sign up for a subscription, right? Something that's actually profitable to the business. And sometimes they won't. So the question is, can we model this process from a narratively generative perspective? We have people visiting or engaging with a business. It can be through the internet here, or we could also imagine this being about in-person engagements. Somebody walks into a store. How likely are they to purchase a product versus walk out without purchasing a product? And you could even imagine trying to abstract this to a more scientific perspective. One animal goes into one environment. Does it do something in that environment, or does it leave without doing something? So it's a pretty simple mathematical structure, which we can interpret in a lot of different ways. But just to provide a common scope here, I'm going to be thinking about this business application. We have a whole bunch of data on customers who have engaged with the business before, and we have data on whether or not they converted in some way or they didn't. And again, that conversion is, did they buy something? Did they subscribe to something? Did they provide information? Whatever the business is interested in with that customer base. So now let's switch to the case study. Nope. Okay, there we go. And so here I just described the story we just told, right? That there's some kind of customer base, there's some kind of business, there's an engagement between the two that can sometimes lead to a conversion and sometimes doesn't. And so our data will largely be these binary variables. We'll have a 1 if there's a successful conversion and a 0 if there's no conversion. Now, conversion itself is not necessarily a simple process, right? You can already start imagining, brainstorming all kinds of different stories about why people convert. There can be an entire complicated mechanism for an individual liking or disliking certain features of the business, or liking or disliking certain parts of the engagement, or even the product of interest that's being presented. And all of those can interact with the local environment of the business, who else might be there, what the person's feeling based on the previous experiences in the day or the month, and the like. So Are there demographic differences? Are there market differences? Are the geographic differences and the like? But to avoid being overwhelmed, we're going to start simple. We're going to start with the simplest possible story of how customers might convert, and then we'll expand that story based on whatever additional information might be available, and any kinds of problems that we might encounter in the modeling process. Now, before looking at the data, we're going to set up our local environment, and here we're going to use a few things. We're going to use base R. So I'm just going to clean up some of the configurations of base R. You're welcome to convert this into ggplot or plot9 or whatever you might enjoy. This is just, I'm trying to keep it as simple as possible. We're going to use Stan for our Bayesian inference. So Stan's going to give us two things. It's going to give us a probabilistic programming language that we can use to specify our models. And then it gives us a suite of Markov chain Monte Carlo tools for taking that model, evaluating observed data, and using those the posterior evaluations to inform Markov chain Monte Carlo and estimate posterior expectation values. Now, there's a lot of differing opinions on how you should implement Markov chain Monte Carlo in practice. I have my own very strong opinions, and I have developed a set of tools to facilitate that particular approach. So I do a lot of Markov chain Monte Carlo theory, and so I have a particular perspective on kind of how to do MCMC estimation in a robust way, so that the numbers that we get, we can actually trust. We can compare them to what they're actually computing, and not just take for granted that some messy approximation is good enough. And so there's two tools that will facilitate this. The first is these visualization tools. You can find them on GitHub here at this link. Here's the first mistake. The two sources are flipped. So there's diagnostic tools, which are sourced here. And these do things like diagnosing the MCMC output for any signs of inconsistencies, constructing MCMC expectations, and various other kind of tools for following up and studying potential problems. And then these visualization tools that I'm loading here, but are linked to here and described here, these are a suite of tools for visualizing MCMC output. So constructing certain kinds of expectation values, and expectation value related quantities, like quantiles, to visualize more complicated probabilistic structure. And we'll see some example of these being used later on. So with our environment set, we can move on to our data exploration. And that means looking at whatever data is available, right? So we have some logs from previous customer engagements. Now, there's actually three variables here. There's the Y variable that we were expecting. This is an array that contains the outcome of the previous engagements. N is the number of elements in that array. So here we have 1,500 previous engagements. And that means of those 1,500 previous engagements, 859 were a failure. They did not result in a conversion, and 641 were a success, right? So there's a little bit, the probability of a conversion isn't quite 50%. It's not negligible, but there's definitely a bias towards no conversion rather than conversion. Now, this extra variable here that we haven't talked about yet, this is the total previous purchases that each customer has made. So for this particular data set, we're able to track the customers and see how much they've previously spent in this business. The distribution of those purchases can be modeled with a histogram, and the units here are in dollars, and so we can US dollars, and so we can see that there's kind of a preference towards small number of purchases, and then this longer decaying tail of customers who are quite active and have purchased quite a bit. And it's not unrealistic to imagine that conversion probability can be very dependent upon previous purchases. Somebody who has purchased a lot from this company is potentially more likely to engage with that company in the future, and vice versa. Now, one interesting thing in this data set, if we zoom in, if we make the bidding really small, we can also just look at the smallest value, the smallest X values in our data set. We can see that there's no zero purchases. So every customer in this data set has previously engaged. And this is an important thing to keep in mind. that if we're going to use these previous purchases, we're only ever going to be able to learn about customers who have already engaged. We're not going to be able to learn necessarily about customers that are new to this business. And that's totally okay, so long as we can communicate that limitation along with the analysis. That what we're really modeling here is how existing customers behave, and not necessarily how new customers behave. Unless, of course, we're comfortable making the assumption that new customers behave just like customers who have made a small number of purchases before. Now, to get a sense for how the conversion might vary with these previous purchases, what I've done here is looked at the empirical frequency of conversion, the number of conversions divided by the number of customers, but binned in intervals of previous purchases. And so we can see that as we go from small number of purchases to larger purchases, there's definitely some variation here. And we can imagine this variation is, due to all kinds of complicated behaviors. The challenge of just looking at data, however, is that we have no sense of whether or not this pattern is systematic as a consequence of some underlying behavior, or it's just a random fluctuation in the data. Right? We need a sense for what kind of variation can there be, and for that we need to actually build a model.
One little
and
question.
So the next step, oh, sorry, go ahead.
One little question. In the previous plot here, we are plotting the previous in dollars per choice. I don't know how to, for each individual or each action of buying something.
So every data point here where we have an X and a Y is an interaction.
An interaction, okay. So maybe there is.
So it's a particular engagement.
Okay.
So at this point, it's ambiguous whether or not one individual could be in the data set more than once because they've engaged multiple times.
Yes.
Versus whether or not every observation corresponds to a unique individual.
Okay.
And this is, I think, it's not necessarily an intended ambiguity, but I think it's a really nice demonstration that we want to be really careful about what we know about the data and what we don't. Here we know there's these XY pairs, and we have a sense for what kind of information they contain. We don't necessarily know the full story. And if that detail is important, then we want to go and research the provenance of this data. Where did it come from? Who pulled it from a database? Who's been collecting it? And ask them, are these individual customers, or can customers repeat themselves? And if so, can we get data on those individual customers? Because that would allow for another kind of complexity in the model. So here we're going to either assume that every individual is different, or that it doesn't really matter whether there's multiple individuals. We're going to model it all the same. And that's an assumption. That's a story. That story might not be right. And if we have access to further information in the future, we can critique that story. And it's always great to keep these things in mind. And what I really like about the narratively generative perspective is it really just facilitates us to ask these questions and think about things we might have otherwise taken for granted, right? This isn't a Kaggle experiment where you just take data and plug it into some code. We're looking at the data, we're thinking about what it means and where it came from, and that alone, that small little difference in perspective, can make it much easier to start thinking about, oh wow, this thing happened, and this thing could have happened, and this thing could have happened, and that's your brain naturally brainstorming, and that's what we want to leverage, right? That's exactly where we want to go. So for our first model, we're going to assume that all of these engagements behave the same. And this is either because the customers behave identically, the customers behave identically, whether they're different customers or it's the same customer coming to the store more than once. So this leaves us with a Bernoulli model. Because we've coded the outcomes as ones and zeros, then the only model for this process is a Bernoulli, and parameterized by some probability parameter theta. So theta is the probability of converting. The higher theta is, the more likely we are to convert. The smaller theta is, the less likely we are to convert. Now, the question is, what kind of prior model do we want to impose on theta? If I want to elevate this observational model into a full Bayesian model, I need a prior on what values of theta are reasonable. And again, we have to rely on our domain expertise. Now, when I'm prior modeling, I don't get too precious, because the reality is prior modeling requires time and effort. There's no way in a finite amount of time you're ever going to perfectly elicit, extract your precise thinking on a subject and then distill that into an explicit mathematical representation. All we really want to do here, or all I really want to do in most cases, is suppress the more extreme behaviors. Behaviors we're pretty confident are unreasonable, and then let the data do the rest. And so that means I want to think about thresholds. What values are reasonable? What values were unreasonable? And in this case, let's say that hypothetically, we're pretty confident that the conversion probability is less than 1/2. It's somewhere between 0 and 1/2. It's not that conversion probabilities larger than 1/2 are impossible. It's just that if they were larger than that, we might be in a different business altogether, right? Like, our knowledge of this business implies that they're doing okay, but not necessarily great. And I can incorporate those bounds with a beta prior, a beta density, chosen so that 99% of its probability is allocated between 0 and 1/2. And that's done with a 0.5, 5.0. So I just kind of tuned this by hand until I got the right upper quantile. And so we can see that it peaks at 0, and then it decays. And by the time it gets 1/2, it's exhausted 99% of the probability. There's just 1% of the probability left to sneak out towards larger values. So this will influence our model, our inferences away from these more extreme behaviors, but they don't exclude them entirely. So if we run into a problem where there's some disagreement between the data and our domain expertise, and the likelihood function, for example, really, really wants the values to be, say, 0.8, that will be allowed. And we'll see that in the posterior, and we can identify that disagreement and follow up on that, try to understand why there's a disagreement. Whereas if I put a prior that was just hard-coded 0 to 0.5 and disallowed all values above 0.5, I would never know that the likelihood function wanted to go higher. So soft containment is what I referred to, this to. And for more discussion on this entire philosophy, you can check out section 3 of my prior modeling chapter here. Go into much, much more depth about why I like these kind of priors and how to construct them. So the introduction of a prior model elevates our observational model into a full Bayesian model, right? This gives us this joint distribution over all of the variables and all of the data variables and the model configuration variable. And we can represent the structure of that full Bayesian model, the structure that we've used to tell the story so far, as a probabilistic graphical model, as a directed acyclic graph. We have our parameter theta. It informs each of these y's, but it does so independently. And that's what this plate notation means. This plate just means that we have separate arrows going to each y, and there's no arrows between any of the y's. So we have two ways of representing the same model. And now we have a third way. The third way is with probabilistic programming. So I can represent this model in math, which I've done. I can represent it visually, which I've done. And now I can represent it programmatically with code. So what a stand program does is just gives us another way of writing down a full Bayesian model. And this is an important thing to keep in mind. In a stand program, you're not writing down a likelihood function. You're not writing down an observational model. You're not writing down a prior model. You're writing down the full Bayesian model. The data block is where you define your observed variables. The parameters block is where you define your model configuration variables. And the model block is where you define the entire full Bayesian model. And so we can see here we plug in the number of observations, the observations themselves. We put a constraint here to indicate that it's can take on values of 0 or 1, but nothing else. And Stan will also check that to make sure there's no kind of contamination in the data. Our lone parameter theta is a probability parameter, so it's bound between 0 and 1. We have our beta prior for that. And then we have our observational model. We loop over each observation, and we add this Bernoulli density function. Now, in practice, if you want the most optimal Stan program, you wouldn't loop. There's a vectorized way of writing this all at once. I'm erring on the side of clarity here rather than optimization. So don't think of these as like the most top recommended style for Stan programs. There are more optimal ways of implementing the same program. But we want to avoid premature optimization. Write the program you can understand first, and then worry about optimizing it. Now, one thing that is new here is this generated quantities block. And what the generated quantities block does is allow us to generate additional information after we've generated a new point in the model configuration space. And the key thing I'm going to do here is I'm going to generate posterior predictions. So for every sample of theta that I generate, I'm going to generate an entire data set. And I can compare these posterior predictions to the data that I've observed for consistency. The only problem with that is that if I have a 1,500 observations, am I going to make 1,500 plots? How do I compare these 1,500 binary values? So instead of trying to compare the entire spaces, I really want to compare summary statistics. I want to somehow find these interpretable properties that isolate certain behaviors and compare to make sure that my predictions are matching the behavior of that summary to the observed behavior of that summary. So for example here, because I don't have any other structure in the model, one thing I might look at is p-hat, the empirical conversion frequency. So it's just, we can think of it as the mean of the y-preds, or it's really just counting the number of successful conversions divided by the total number of engagements. So we run our model. And so Stan, when we run Stan, it's going to take the model, it's going to plug in the data to give you a normalized posterior density function, and it's going to pass that density function to Hamiltonian Monte Carlo, which is going to run this very, very efficient exploration of your posterior, capturing all of those model configurations that are consistent with the observed data and the domain expertise in the prior, and return those values. Now, to make sure that those values are a faithful representation of what your posterior actually looks like, we want to check our diagnostics. These are my recommended diagnostics. We have diagnostics that are specific to HMC, and we have diagnostics that are kind of more generic, that apply to any MCMC algorithm. In this case, there's no problems. Both of those are passing, so we have nothing to worry about. Which means we can move on to the next step of evaluating our model, which are the retrodictive checks. So before looking at any kind of posteriors or any inferences, I want to first compare the model predictions, the posterior predictions, I should say, to the observed data. Because if my model is not adequate, if it's too rigid, then the model might be contorting itself. And so the parameters wouldn't mean, they wouldn't be interpretable the way we think they're interpretable. So before being potentially confused by our inferences, we want to check our adequacy. So we have the statistic that we computed already in the generated quantities block for our predictions, for our posterior predictions, where we sum the number of ones and then divide by the total number of engagements. Now, for the observed data, I'm going to have a single value of this, right? I take my data, I plug it into the summary, I get a single summary value, and that's the black line here. But on the posterior prediction side, I have a lot of values. There's uncertainty in what that posterior prediction should be. And what this code here does is it visualizes the distribution of those posterior predictive values. The red is the Markov-Chain Monte Carlo estimate of this interval probability. The gray is the MCMC error. So it's our computational error. And this allows us to kind of gauge what's a meaningful structure, what's meaningful shape, and what's just a computational artifact. Right? Any kind of noise or feature within the gray bands, not trustworthy. And what we see here is there's perfect agreement. our posterior predictions line up with the observed data. In other words, there's no retrodictive tension, right? This isn't a predictive test here. It's not a predictive comparison, because I'm not comparing my predictions to something new I haven't seen before. I'm comparing it to the data that already went into the model. So it's a retrodiction, as opposed to, say, a post-diction. Or sorry, it's a retrodiction or a post-diction as opposed to a prediction. Here I'm following the notation of Good, I.J. Good. He and George Box, my favorite old statistics writers. It sounds pedantic, but I think it's important to separate out and make sure that we're not misinterpreting what we're doing here. So our models' predictions are able to reproduce the behavior of the observed data, at least when it comes to this particular statistic. But there's a lot of other statistics that we might also consider. For example, what if we want to test the potential dependence of the conversion probability on previous purchases, right? It's not in the model. And maybe it's a problem it's not in the model. So to do that, I'm going to take those posterior predictions, I'm going to bin them in intervals of previous purchases. So we'll have bins going from $0 to $6,120, and each bin is $153 wide. And in each of those bins, I will construct posterior predictive values, many of them, and then I will convert that ensemble of posterior predictive values into these quantiles to represent the posterior predictive distribution. There's a lot going on here, and if you're curious about how this is actually constructed, I'd recommend checking out this link. I have a full figure that shows how this is done incrementally, step by step. But the basic idea is this gives us a way of investigating the potentially conditional behavior that manifests in the observed data. And indeed, we see that the observed data shows this kind of fall off, that the conversion probability conversion frequency is larger for larger previous purchases, and it's smaller than smaller previous purchases. Our posterior predictions, on the other hand, are flat, which makes sense because the conversion frequency is the same. We're not taking into account previous purchases. Now, the real killer feature of these posterior retrodictive checks is that we can use the posterior predictive uncertainty to quantify what a meaningful deviation is and what a non-meaningful deviation is. Right? You'll notice here that we get smaller previous purchases, we get wider and wider posterior predictive uncertainties. That's because there's less data in those intervals, so that we have a less of a constraint about what's going on out there. When I go to smaller previous purchases, I have much narrower posterior predictive uncertainties. And the behavior of the observed data is deviating pretty far outside of those posterior predictive uncertainties. And so we're looking here, it's not perfect agreement. We just want to see the data within those red intervals. And we're not really seeing that. And so this suggests that maybe there's some dependence with previous purchases that we want to model. Now, at this point, we're suspecting that our model's not quite right. We're skeptical. And we could immediately go to improve the model, which is what I'd recommend in general. If we tried to look at our posterior inferences, we have to be really careful in interpreting them. Because what happens when our model is inadequate, when it's too rigid, when it's not flexible enough to capture the behavior of the observed data, then what it tends to do is distort itself. It kind of contorts to match the particular behavior of our particular observation. And that contortion isn't going to generalize, right? The way the model contorts itself is going to be different for every possible realization of the data. And that means that these parameter values are going to get thrown all over the place. And they're going to tell us how the model's contorting, which isn't anything meaningful, right? It doesn't correspond to what's actually happening with the underlying data generating process. Here what we see is that our posterior inferences for theta, not our predictions, our actual inferences, are concentrating on pretty large values. And it looks like it's actually fighting against the prior, right? The prior is the only thing keeping that posterior from going to larger values, which isn't surprising, because a lot of times when our models are not rigid enough, or too rigid, they're not flexible enough, the contortion they need to best fit the data goes outside the scope of reasonable behaviors. It goes into the tails of the extremes of the model configuration space. And our prior is fighting against that. So we can plot this, we can see that kind of tension between the prior and the likelihood function. But again, we don't want to interpret this too strongly. We know the model's not adequate. We know that it's missing an important feature. We don't want to take this behavior too seriously. So in general, I would recommend not even looking at your posterior inferences until you have adequate retrodictive checks. But this is an example of what kind of behaviors you might see if you did. So what are we left to do? Well, the advantage of posterior predictive, the advantage of posterior retrodictive checks is that not only do we know there's a problem, or not only are we suspicious that there might be a problem, I should say, we have a sense of what the problem might be. We saw previously that the data seemed to show variation of conversion frequency with previous purchases that our model wasn't able to reproduce. So this suggests that we want our conversion frequencies, and in turn means our conversion probabilities, to vary with previous purchases. Now, there's a lot of ways that we could try to model this. We could try to model y and x jointly and have some complicated relationship for how they get generated that induces some dependence of theta on x. Here, I'm going to take a more heuristic approach and say that I'm pretty sure that theta depends on x, and the behavior of x itself doesn't really influence that relationship. And the regression context would say there's no confounding here. So I can model how x influences theta without having to model how x itself behaves marginally. And that suggests a model like this. So I replace the parameter theta, that one variable theta, with the output of some deterministic function of the previous purchases. And this will allow theta to vary with the previous purchases. The graphical model looks like this. Theta now becomes an output of some deterministic function. So I use the dashed line to denote that. We have our observed x's here. I'm using the box because I'm not treating this as data. They're just a fixed input. And I'm not modeling where the x's are coming from. Whereas the y's will be data, but I'm going to model where they're coming from so they get a proper circle. And then we have this new parameter phi, which configures the behavior of this functional relationship. Now, to complete this model, I need an explicit functional relationship. And there's a lot of things that we might appeal to here. We can try to think about very flexible functional models. We can go to Gaussian processes, hell, even things like neural networks or VAEs if you really wanted to go down that path. But just like with the other parts of the model, we really want to leverage as much domain expertise as possible. And in this case, this means thinking about what kinds of functional behaviors are appropriate. How might the conversion probability vary with previous purchases? In this case, let's say that we're pretty confident that the more somebody spends, or the more somebody has spent in the past, the more likely they are to convert in the future. So there should be some increasing relationship. As previous purchases gets bigger, theta should get bigger. But it's not a linear growth. At some point, that increase starts to saturate. We start getting diminishing returns. There's only so much, high of a probability that somebody might convert with. Now we can capture that behavior with a functional form like this, where there's some kind of saturating function. So it starts off kind of growing linearly, and then it turns over to get flat. And then we have some parameter psi1 that controls just where it saturates to. And of course, we can write it in code, just as giving us a second way of thinking about this as such. So the structure, the form of this functional model already restricts the kind of behaviors that we might encounter. But we still have to introduce a prior model as well for phi1 and phi2 that further restricts those reasonable saturating behaviors. So for example, I can think about psi1 and psi2 independently of each other. That's one advantage of this functional forms. They're really controlling two different behaviors. Psi controls where it saturates to. Sorry, psi1 controls where it saturates to. Psi2 controls how quickly it saturates. So I can think about building a prior model for these two things separately. This isn't always true. Sometimes we have behaviors that are very highly coupled, and it's best to think about them jointly. Here it makes sense to think about them independently. Now, when it comes to constraining what the asymptotic conversion probability is, we can use the same domain expertise that we've already used. Let's take what we thought about the monolithic conversion probability and apply it to psi1. Worst case, this is just going to be a kind of conservative bound on what could happen. Psi2 is a little trickier. For psi2, we need to think about how quickly things can saturate. Do we reach maximum conversion probability after $10 of purchases, or does it take thousands of dollars of purchases? One way of trying to interpret the consequence of psi2 is to think about a half-life. At what previous purchase do we achieve half of the maximum conversion probability? And it turns out that half-life is given by psi2 over log 2. So in other words, if I have a sense of how much somebody has to purchase before they get halfway to the maximum conversion probability, that gives me a sense for what psi2 should be. And in this case, let's say that I'm pretty confident that after about say about 2,000 US dollars covers around 5 of these half-lives, a 5-fold of the half-life, if you will. In other words, that the half-life is something larger than 400 US dollars, right? I'm just taking whatever I happen to know and translating that to this half-life, this purchasing power. And I can plug that into my relationship between x1 half and psi2, and that gives me a bound, approximate bound, that's all I need, on the reasonable values for psi2. And taking care to pay attention to the units here, we get something where we want psi2 to be around about less than 2, not US dollars, not US dollars, not 1 over US dollars, but 1 over kilo US dollars. And so keeping track of the units here, we might do something like a half normal prior that contains the values of psi2 between 0 and 2, and we do that with a little scaling here. So this half normal allocates 99% of its probability between 0 and 2, just like we were doing with the beta. And again, for more details on how to do that, I have much more discussion in my prior modeling chapter. All right, so we've expanded our model, introduced this functional form, and thought carefully about the reasonable behaviors of that functional model so that we can build our principled prior model. And we didn't have to get too precious here, right? We don't need precise information. We don't need to be perfect. We're just trying to get rough scales of where things get weird. Now, the prior on psi1 and psi2, we have spent some effort to make sure that they're reasonable. We've gone through the effort to try to distill the individual behaviors they moderate and what we know about those behaviors. But those behaviors do get coupled, right? The functional form that we draw depends on both of these parameters at the same time. So just to make sure that the consequences of this prior model are reasonable, there's not any kind of unexpected consequence, we might want to look at some of those consequences. And so what I can do here is I can simulate from the prior model, simulate a bunch of psi1 and psi2s, and draw this conversion probability function for all of those samples, and just to make sure they're reasonable. And so we would compare this to our domain expertise, and let's say that it does look okay. Now, it might not, right? You might see that there's occasionally a functional form that shoots up way too quickly, or it saturates at too large of a value. In some cases, we might know something with the lower bound of the saturation of the maximum conversion probability. And we might see that we don't achieve it fast enough, or we achieve that too quickly. So this just gives us another way of looking at the consequences of our assumptions, just to make sure it doesn't conflict with any other domain expertise that we haven't included in this model yet. We're just looking for surprises. And here, fortunately, we don't see anything. So now we go to our second model. We have to implement this functional form. We add the x's into our data now. We expand our parameters block to include psi1 and psi2. We put both of those priors in. Notice I'm putting the units everywhere. This is one of my favorite things to do. I love putting units in comments. It really makes it easier to track down the provenance of what everything means and avoids errors and confusion later on, especially when I'm using different units here, as you might notice. So the x's are in units of USD, but this psi2 is in units of 1/kilo US dollars. Because if I did it in 1/US dollars, it'd be way, way too small. It'd be a really, really tiny number. And putting it in units of 1/kilo US dollars means that its natural values are closer to 1. And then I correct for that here by correcting from kilo US dollars to US dollars, right? And why I'm doing this makes sense when I have this information here and here. And then the model is pretty much the same. It's just instead of having that theta, I have psi1 and psi2. So we run, no problems with the diagnostics, and we go straight to our retrospective checks. That aggregate check that looks at all of the behavior at once looks good, just as it did before. And this is an important thing to keep in mind. Even though we don't think we've changed anything that would affect this particular behavior, we still want to check, right? A lot of times when we expand a model, add some new functionality, there's unintended consequences. So think of these retrodictive checks kind of like unit tests in software engineering. Once you do it once, you always want to go back and run it again and again and again. It's part of your stable of checks, just to make sure that there hasn't been any kind of unintended change to behavior that you previously that had previously been behaving okay. What's more relevant here, however, is that we're getting more flexibility with our posterior predictive behavior. Although arguably it's too much flexibility. The observed data decays a little bit. It reduces when you go to smaller previous purchases, but it doesn't go all the way to 0. Whereas our posterior predictions do seem to go all the way to 0, which makes sense because our functional model went all the way to 0. We can zoom in and see this a little bit more clearly. It looks like the observed data is kind of hitting a different value at 0 previous purchases than our model is. So we've kind of gone too far in the opposite direction. Now, this isn't necessarily a slam dunk, right? You might look at this plot and go like, well, I don't know. There's a lot of noise here. One reason, these patterns here that kind of look like something weird's going on, this is due to the discretization of the frequencies. If I only have 5 counts in one of these bins, then the values I can get are 1/5, 0, 1/5, 2/5, 3/5, 4/5, and 1, right? And so there's kind of a discretization of the black bars here that gets washed out in the posterior predictions. But let's say we're worried about this, right? That we happen to see this and we start going, okay, something weird's going on. There's something that is giving us a higher conversion probability or higher conversion frequency here at smaller previous purchases than we really think the model's capable of. And we can take that suspicion and use it to motivate a new model. And this is a really important thing to keep in mind with these iterations here, is that we don't have to be confident that we really need to improve things. If we take a model and expand it, and the new features don't help, our inferences are just going to go right back to the initial features. So we have a little bit of a safety here, and that if we're suspicious, we think something might be happening, but we're not sure, it doesn't hurt to just go one more iteration, add that new functionality, and see if things improve. So in this case, we have a suspicion about the general behavior. We don't necessarily have a suspicion about what could be causing it. But let's say that we're grumbling about this problem. We're not quite happy with our fit, and we're mentioning it to a colleague over lunch. And they happened to mention that, hey, did you think about these VIP customers? And you go, what are you talking about? They're like, you know that we get a bunch of customers who are coming to our website or coming to our business, not because they've shopped with us before, but because they're really excited in the promotions that we're offering. So, for example, the business that we're working with here, they might be offering a Copa America promotion, and because of that, they might get customers who are big football fans, but aren't necessarily super into the product initially. And these different kinds of customers would then be contaminating the data, because their propensity to convert with this engagement isn't going to depend on previous purchases. They're just there because of that promotion. So they're there for a different reason. They behave in a different way. One thing I think this really nicely demonstrates is that our domain expertise is not this static thing. Our domain expertise is this implicit knowledge that we have, both internally and then within our collaborators, within our community that we're working with, within the field that we're in, within a client, if you're in like a consulting engagement. And that means that the knowledge you start building your models with, the stories that you tell initially, might be completely compatible with the domain expertise that you have elicited, but it doesn't mean that's going to be all of the information you'll ever consider. As we're iterating through and we see new features and behaviors in the data we weren't expecting, that might trigger additional domain expertise that we hadn't yet considered. That might trigger discussions with collaborators and clients and the community who might provide information we weren't aware of initially, right? And this is just an example of something like that. And this is okay. This is not a problem, right? Getting more domain expertise after looking at initial fit is not using the data twice. So long as what we are gaining afterwards is not informed by our fit itself, but rather additional knowledge based on our follow-up and discussions about that initial model, right? We think about the initial fits are triggering knowledge we already had, but hadn't considered or hadn't employed. So with this additional boost of knowledge, that there's this contaminating community that behaves differently, we have a sense for what we want to do with our model. We have our data generating process for the typical customer. And then we have the second data generating process for these important customers. We'll call them VIPs, right? People who say are interacting with this business because of that promotion. And because of the way they're interacting, we don't think that that their propensity to convert would have anything to do with previous purchases. They're just going to have some flat conversion probability, similar to the first model that we worked with. Now, the only challenge here is that we don't know who's who. We don't know if a particular customer, a particular engagement, we don't know if a particular engagement is dealing with a customer who came in because of that promotion, or is a customer who's coming in because they're looking for a product because they already want to purchase something. And the way we incorporate that uncertainty is what's known as a mixture model. And so mathematically, we have something like this, which the highlighting in Cordo is kind of a mess, so I apologize with that, for that. But we basically allow there to be some probability of every customer being a VIP customer or a regular customer. And this lambda parameter here basically quantifies the proportion of VIP customers versus those relative customers. So our model expands. We have to include a theta VIP and a lambda for not just modeling how these new customers behave, but how we incorporate those new customers into our existing data generating process. Of course, we need a prior model for these new behaviors. Here, I'll take a flat prior model for lambda. Let's say I'm not really confident about there being a lot or a small number. I don't know how much money went into the marketing of the last campaign, last promotional campaign. So we're going to keep that pretty diffuse. And for theta VIP, let's do the opposite of what we did with theta conversion. We're pretty confident that we want theta VIP to be above 1/2 because these customers are much more likely to engage due to the reason they're in that store. So our model then looks something like this. We have that same functional form. We have psi1 and psi2 as before, but now we have lambda and theta VIP. We have the priors for lambda and theta VIP. And then our observational model has to mix these two things together. And this log mix function is just taking the individual likelihood functions, weighting them together, and then, it takes the log likelihood functions, it exponentiates them, weights them together, and then takes the log of that, because Stan deals with the log scale for everything. In our generated quantities block, we have to keep this data generating process in mind as well. When we're looking at a particular n, we have to flip a coin to see if that particular observation came from a regular customer or a VIP customer, and then simulate a conversion accordingly. We plug it into Stan, we run, we check our diagnostics, and we come to pain. Now you'll notice here that the regular diagnostics don't show any problems. It's just these HMC-specific diagnostics. And what I love about Hamiltonian Monte Carlo is that when it fails, it's extremely sensitive to its failures. If HMC is not able to explore all of your posterior, there are observable consequences to that. And we can turn those observable consequences into these diagnostics. So these divergences are indicating that there's some part of the posterior that starts getting kind of narrow, and it's preventing the sampler from exploring any further, which is truncating the actual posterior uncertainties. And we can look for that by looking at pairs plots. I take every parameter, every pair of parameters, I plot them against each other, and I color the stable, the non-divergent samples differently from these problematic divergent samples, which are shown here in green. And you can see there's a lot of non-spherical looking uncertainties, which is not necessarily a problem until we get down here to the bottom right. Notice that those green dots are kind of piling up down there at the bottom where things are pinching together. Right? There's other places where the posterior pinches a little bit, but it's only one place where we're getting an excess of those green dots. And that suggests that there's a problem at those green dots, that there's actually more posterior that the sampler can't reach. Right? We can zoom in and see this a little bit more clearly. So there's two things we can take away from this immediately. One is that there's potentially more uncertainty here we're not capturing. Two, we get a sense for what that uncertainty is, right? This is lambda and theta VIP. What we're seeing here is there's a really strong degeneracy in this model. Lambda can get larger so long as theta VIP gets smaller. There can be more VIP customers so long as they are less likely to convert. And there can be less VIP customers so long as the VIP customers that are there are much more likely to convert. The data can't distinguish between those two possibilities. So our Bayesian posterior is trying to encompass all of those possibilities that are consistent with the data, but it's running into a computational block. And one way we can try to resolve this is by changing how Stan's HMC sampler works. We can try to make it less aggressive. Technically, we work with this adapt delta configuration. This changes how aggressive the adaptation of the sampler is. We'll go from the default of 0.8 to 0.99, make it less aggressive, and that should lead to a more expensive fit, but one that might be able to explore more of that posterior. And interestingly, when we do that, there are no problems. All of our diagnostic problems have gone away. And we can see if we compare this new posterior to the previous posterior, a substantial difference. So the light red is what we got with the default Stan settings. The dark red is what we get with this tweaked adaptation. And you can see there's a lot more model configurations. There's this really, really narrow tail that keeps going. And so if we had ignored these diagnostics, we would have gotten an unfaithful, an inaccurate picture of what's actually going on. But because there are no more diagnostic issues, we're pretty confident that this dark red is actually giving us a faithful characterization of our posterior uncertainties. And that means we can look at our retrodictive checks, which look great. Both of them look great. You can now see that our posterior predictions have gone from being flat to being too small to now being somewhere in the middle. It looks like this admixture, this contamination of the VB customers is doing what we want it to. And now we can finally look at our individual inferences, right? Now we have this is our first model where our computation is accurate and our retrodictive checks look good. So it looks like our modeling assumptions are good enough to capture the behavior of the data we've collected. The only problem here is there's a lot of uncertainty, right? You can see Psi1 and Psi2, we're learning a little bit about them, not a ton. We're getting a decent information about lambda, but theta VIP, for example, is basically the prior. We're not learning anything about theta VIP from the data. So one thing that is always helpful when you're dealing with complex uncertainties is adding more information. And from a Bayesian perspective, we have two routes of adding information. We can add information through the prior model by eliciting more precise information and using a narrower prior model for all of these individual parameters, or at least some of the parameters. But we can also add information through the observational model. We can repeat our measurements over and over again, or even better, we can add extra data. Data that's sensitive to these underlying behaviors in different ways. And that might be able to compensate for the degeneracies of our initial data generating process. So here, for example, we're having a hard time separating the VIP from the non-VIP customers. What if we had a way, we had data that was sensitive to just the VIP customers? Well, let's say in this case, we're again grumbling about our analysis, and one of our colleagues is like, "Oh, you know, there's logs for that, right? You know, there's a promotion that we ran where you had to be, say, like a member of a fan club or something to get it, and we know who did that." So this is a separate data set that goes outside the scope of our initial data set, and it's only sensitive to one of those two data generating processes. And we can incorporate that auxiliary data. We have a separate data set, separate set of logs. You can see there's much fewer observations in it, but there's many more conversions than there are non-conversions, consistent with this being a more inclined to convert population. Now, to incorporate this into our model, we need a third data generating process. We need to take our model for the two data processes that mix together to model our existing data set, and then a new data generating process to model this auxiliary data. And conveniently, because that data just depends directly on theta VIP, it's a pretty simple addition, right? We just add this box above theta VIP, or add this new term here in brackets, which again, I'm not going to be able to highlight separately, but it's the second to last there. So now we're adding more and more data generating processes, which allow us to incorporate more data, not because, for any kind of model inadequacy reasons, but rather because we want to get more precise posterior uncertainties. And it's not always possible to repeat the experiment. Sometimes the best thing that we can do is to add this auxiliary data. So our standard program, again, pretty straightforward. All we have to do is add this additional data in the data block. Add this separate data generating process. So we have this separate set of data that we loop over and model it. And then our generated quantities block, not only can we make predictions for our first data set, we can also make predictions for our second data set. So we want to do retrodictive checks on both of those to make sure that the thing that we're adding is being modeled adequately. It looks like something has changed, because in the default settings, we don't get those divergences anymore, which is a good sign that our posterior uncertainties have improved. Our retrodictive checks look good, both for the initial data set and for this auxiliary data set. And then both for the aggregate behavior and the conditional behavior. So we've added additional structure, and we've verified that we're modeling it adequately. This leads us to looking at our inferences. Now, I'm going to compare on the left the previous model, and on the right this new model that's incorporated this auxiliary information. You can see that Psi1 and Psi2 don't improve that much. There's a little bit of improvement, but it's not a ton. And the reason for that is that those are also pretty degenerate. So if I increase the maximum conversion probability, Psi1, I can fit the data just as well, so long as the saturation Psi2 gets smaller. Equivalently, if the maximum of that curve goes smaller, I can fit the data in a similar way, similarly well, I should say, so long as Psi2 gets larger. And we can translate this to interpretable functional behaviors, right? If psi1 is larger, then the peak goes up. And if psi2 is smaller, then it takes longer to reach that peak. So I'm going into, this more like a kind of linear-like shape. And if psi2 gets smaller, psi1 gets smaller and psi2 gets larger, then I'm very quickly turning on and then getting flat. So you can kind of see that we're getting a line and we're getting a straight line, and they're kind of like averaging and looking kind of the same. We don't have enough data to separate out those behaviors. So if I wanted to improve this, I might consider a more informed prior model for psi1 and psi2. I might imagine data that's only sensitive to the regular customers. Maybe I have data on, or even getting more data for high previous purchase customers, because that's really where I can constrain what's happening with the saturating behavior. And I can use the structure of these uncertainties, the interpretation of the model, to motivate how to do better, what information I need, and how I might want to expand the model in the future. Our inference for lambda get a little bit better. You can see this kind of upper tail kind of values around 0.4 get suppressed with this additional data generating process, which makes sense. We're able to better separate out these two behaviors. The big thing is theta VIP, right? We have additional data that's directly sensitive to theta VIP. Unsurprisingly, we get a lot more information about theta VIP. So everything's kind of behaving as expected. So at this point, we spent most of our time trying to expand our model to accommodate either the features we need to fit the data reasonably well, or the data we need to get sufficiently precise inferences. At this point, if we're pretty happy with how things are going, we can now start considering what we want to do with this information. Why do I want to learn about theta, the conversion probability, and theta, the VIP, the conversion probability for these VIP customers? What's actually relevant to the decisions that I want to make? If I want to put a new promotion out, if I want to reconfigure the store, introduce a new product and the like. Well, let's say in this case, what I care about is the regular customers. I want to design something. I want to optimize something relative to how the regular customers behave. And the tricky thing here is the regular customers don't actually correspond to any of the data generating processes that we've considered so far. Right? The mixture data generating process, yeah, it has the regular customers in there, but they're contaminated by the VIP customers. And this auxiliary data generating process is all VIP customers, has no regular customers in it. If I want to model and isolate the regular customers, I need to just look at the X-dependent conversion probability model and nothing else. I want to remove that contamination. And fortunately, that's straightforward to do. Again, I just think about adding another data generating process. In this case, it's a data generating process. It depends on psi, depends on these hypothetical pre-purchases, but it doesn't depend on lambda, and it doesn't depend on theta VIP. So I can now make counterfactual, generalized, out-of-sample predictions that take advantage of some of these behaviors, but not all of them, right? I can think about intervening and removing the VIP community. What does that mean? It means this. Now, I do have to choose the X's for these hypothetical predictions. If we're modeling the X's, then we could use that model to simulate new X's. Here, I can take advantage of the fact that I'm free to choose the X's and think about, for example, a uniform grid. Because I want to study what happens across purchases, and I'm not limited to the decaying purchases that we have in the past. If I want my predictions to be just as informative for small purchases as they are for large purchases, then I'm going to choose a grid that's balanced across all of those. And now I'm not going to get that kind of increase of posterior predictive uncertainty at larger purchases, larger X's, than I did at small X's. So again, I'm really leveraging the hypothetical nature here to engineer the behaviors that I want. And the beautiful thing about the interpretable model is it's straightforward to do that. So the model block itself is all the same. All we're changing in the generated quantities block, sorry, I should say in the data block, we're adding the hypothetical structure. And then the generated quantities block, I am making these hypothetical predictions. So we can run that. Now, at this point, I'm rerunning a posterior that I've already fit. right? The computation is exactly the same. So I don't need to check the diagnostics. I don't do the retrodescriptive checks again. It doesn't hurt to do it again just to double check. But here I'm skipping them because I know I'm using the same exact model. All that I'm changing is a generated quantities block. And this puts me in a position to start comparing all of my predictions. If I made predictions about future conversion frequency based entirely on our first data set, I would get something in the left figure. If I made predictions based on what we saw with the VIP data set, I'd make predictions based on the middle plot. But if I wanted to make predictions based on just the regular customers, I would get the right plot. And it looks nothing like the first two. So by building up this generative model, interpreting all of these structures, all of these individual features, not only do I get principled inferences for the data that I've collected, I'm now in this position where I can start adjusting the model as needed to make predictions in all kinds of new circumstances. I could similarly make predictions for just VIP customers. I can imagine different kinds of contamination. I can imagine new kinds of customers entirely. I can imagine customers that just have a large previous purchases, just have small previous purchases. It's all a possibility. It's all straightforward because of this generative structure. So this is just an example. It's intentionally simple so I can get through it in just over an hour. Thanks for staying a little bit late, everyone. It's meant to demonstrate these ideas of interpretable generative models, as well as some of these auxiliary ideas about things like retrodictive checks, prior modeling, prior checks, and the like. Because when it comes to implementing them, they all get integrated together. There's a ton of links that go into additional details if you want to further explore. And I also have some additional examples on my website that go into more complicated examples where you start seeing, okay, this seems pretty straightforward, but now let's just turn the crank and get real complicated with it. And that's really where you see the power, where you're not getting something that you can run in an hour, you're getting something that takes months to develop. And then for those who may want to, so first, I guess thanks to all of my Patreon supporters who help make stuff like this possible. If anybody wants to run any of this code or play with it, it's all here. So there's a GitHub link down here to the repository with the data, the markdown code, as well as all the stand programs separated. So you can kind of mix and match and do whatever you like. And then you can also see our environment here if there's any kind of disagreements with what you might run locally. With all of that, are there any questions about this demonstration here?
I don't have any question. I want to test it.
It's either really good or really bad.
No, yeah, really well, really well. Yes, it's a great example.
Cheers.
A deep example with all the details.
Well, they're all deep examples, right?
Yes, no, but with all the details, with diagnosis of conversion.
Yeah.
Thank you very much.
Yeah, thank you so much, Michael. I think that from my side, not coming from the mathematical programming and inside computational tasks, this it was maybe a little bit difficult, but it was really great to see how everything is going like really step to step. I mean, it gave me the hint somehow, and I think that that's my personal key takeaway message. It's like that it's really needed to play with our own data a little bit more, because maybe there is something extra to tell. Maybe there is a really story on the background that we don't know. I really like this example of, okay, suddenly you just came up with VIP customers and then you have a totally different story. So from my side, thank you very much. And I think that it makes me really enthusiastic to go back to my data in the ecology side and to say like, hey, okay, what if there is something I've not seen? And I think that that's also the key for using Bayesian methodology to applications into any research. So once again, thank you.
Yeah, I do a lot of ecology consulting in collaboration, and so there's a bunch of examples in that direction I can also point you to if you're interested. I do want to comment, if any of this material does seem, kind of like technically overwhelming, which is absolutely possible. One more analogy that we can take from that storytelling perspective is think about these ideas as almost like learning a foreign language, because the language that we write these models in, that we tell these stories in, is math and statistics and code. And just like when you're learning a new foreign language, you're not going to start with the most complicated. You're not going to write a novel, right? You're going to start with those toy examples, and that gives you a setting where you can tell a simple story that requires a relatively simple statistical picture, the densities that you're using, the code that you're using, how you program it in Stan, right? That's how you start, and then you build up from there. And as you acquire more vocabulary and more fluency in the language, then you can start telling these more elaborate stories. So it's very much part of the picture. And I think what I hope this generative picture helps people with is to recognize that the domain expertise is part of this. A statistician can't do this by themselves. You need to have the collaboration, the domain experts and the statistic experts and the coding experts all together collaborating to make this happen. And so even if some of the coding stuff and technical stuff might appear a little overwhelming initially, the story is where we start. And you can do a lot with that initially, and you can build up into that. So the path is there, and it will get easier with practice.
Okay, thank you very much.
Thank you so much for that.
Well, stay here. I
Cheers.
will finish the YouTube transmission, and then we talk.
I want to get the chance.
Okay.
Sorry for a second,
Thank you
and
very
me
much.
maybe
I
also even
want
in
to
the.
say something also. Thank you.
Also, when we keep the transmission, I will just post the link, which is for joining to the Bachelor's community. So go ahead, it's going to help us and also to keep us connected. So yeah, use this link for that. Thank you.
So well, we will be in Salta, in Argentina, the next 2 weeks. There are some space to. I will speak in Spanish in this moment because it's for here in Argentina and in these countries. Bueno, nos vemos muchas gracias a todos y a todas. Nos vemos en 2 semanas en Salta. Recuerden que si necesitan necesitan habitaciones, lugar donde dormir, la universidad está ofreciendo, así que entren a la página de vallesplurinacional.org, a la pestaña Tu viaje, y ahí van a poder pedir una cama o poder pedir una carpa para estar allá. Thank you very much. I will stop.
Thank you very much
If there is
to everybody. Thank you. And with this, we are going to close then the seminar.
We have some questions
seminar, so thank you.
Before finishing. We can keep talking now, so I will stop the transmission. Thank you very much.
Thank you very much.